Hello there and welcome to Physics with William, where curiosity slows its pace a little and science is allowed to unfold without hurrying you along. Tonight we're settling in with a question that sounds as though it belongs in a very serious laboratory, full of humming machines and people wearing expressions of deep concentration. But it turns out to be the sort of question that can sneak into an ordinary evening and stay with you much longer than expected. What is an antiparticle really made of? It sounds technical at first, perhaps even slightly unfriendly, like the name of something that would not let you sit at its lunch table at school. But underneath the formal language is a surprisingly human kind of puzzle, because it asks how nature handles symmetry, how the universe makes copies, and whether the mirror image of something familiar is built from different stuff or from the same ingredients arranged in a different way. Before we wander too far into that, I would love to know where you're listening from tonight and what part of the day has found you. Are you tucked in somewhere quiet with a lamp still on, listening while the rest of the room fades into softer outlines? Are you at the tail end of a long afternoon, perhaps with rain at the window or tea gone lukewarm beside you? Or are you somewhere bright and busy, stealing a thoughtful little pocket of time for yourself while the world continues being noisy in the background? There is something oddly fitting about talking about particles and antiparticles while people in different places arrive at the same idea from different corners of the world. Same topic, different vantage point. Physics does enjoy that sort of thing, and if this kind of slow scientific wandering is your sort of evening company, if you find it calming or interesting or simply a better alternative to doom scrolling under the blankets, then a like and a subscription would be warmly appreciated. It helps this quiet little corner reach other people, who may also enjoy having the universe explained to them as though we are sitting in the same room trying to make sense of it together. Not with too much fanfare, not with flashing lights and a great deal of shouting, but in the gentler way these things deserve. Now, antiparticles. The word itself tends to make people imagine something dramatic. Anti sounds combative, as if the particle has developed a personal grudge. You hear antiparticle, and you might picture a villainous little object in a cape, standing opposite an ordinary particle with tiny folded arms, refusing to cooperate on principle. But the truth is much less theatrical and much more interesting. An antiparticle is not anti in the everyday sense. It does not oppose existence. It does not lurk in dark corners waiting to undo the furniture. It is not made of some separate mystical substance called anti-stuff. It is, in many important ways, just as real and just as lawful as the particles that make up the world around you. That is part of what makes the topic so compelling. When people first hear that every ordinary particle may have a partner of some kind, there is often a natural response of mild suspicion. A partner made of what exactly? If an electron is a real thing, with real properties and real effects, and an anti-electron also exists, then surely one of them must be the normal version, and the other must be some strange imitation built from a more exotic material. We're used to differences in the world being caused by different ingredients. Bread and cheese are different because they are made of different things. Wood and glass are different because they come with different internal structures and different kinds of atoms. So when physics says that a particle and an antiparticle can be closely related while still having opposite electric charge, the mind naturally wants to ask what changed in the recipe. That question becomes even more tempting because physics often sounds like it should have recipes. We talk about building blocks, ingredients, constituents, and fundamental pieces. The whole subject encourages the image of reality as a kind of cosmic kitchen. One bowl for matter, another bowl for energy, perhaps a rather dangerous cupboard for radioactive items, and somewhere in the back, next to the measuring spoons nobody can find, a labelled jar of antimatter glowing faintly and making everyone nervous. It would be very satisfying if we could say that an antiparticle is made of some hidden opposite ingredient. Ordinary matter uses one sort of flour, antiparticles use another, and nature keeps the two sacks carefully separated until somebody in a research facility makes a terrible mistake before lunch. But nature is usually not that accommodating. Very often, the deepest truths in physics are not about one object being made of different material than another. They're about patterns, properties, relationships, and the rules that govern how things behave. This is one of those cases where asking what something is made of can lead us somewhere useful, but only if we are willing to let go of the ordinary kitchen metaphor when it stops helping. Because for many of the entities we call fundamental particles, asking what they are made of in the usual sense may be a bit like asking what north is made of. The question sounds reasonable right up until you realise you're mixing categories. North is not built from smaller northern bits, it is a direction. It tells you something real, but not in the same way that bricks tell you something real about a wall. Particles occupy a curious place in our thinking. On the one hand, we picture them as tiny things, little objects like grains or specks or miniature pebbles. On the other hand, modern physics does not really permit us to treat the most basic particles as tiny billiard balls with little surfaces and tiny internal gears. They are not small marbles with an inner filling that one could scrape out and inspect under an even tinier microscope. They are excitations of underlying fields, which is a sentence that sounds suspiciously like it was written to frighten away a perfectly decent audience, but it simply means that what we call a particle is not best understood as a miniature bead of substance in the old-fashioned sense. It is a stable little packet of behaviour arising from something more fundamental. That may feel like a lot to put on the table this early, but it is worth planting the idea gently now, because it changes the whole tone of the question. If a particle is not a tiny object with ordinary internal stuffing, then an antiparticle need not be some opposite bead filled with reverse stuffing. Instead, it may be another allowed excitation of the same deep framework, carrying related but opposite properties. Same deeper field structure, different role within it. Same basic laws, different sign on certain quantities. Suddenly the question, what is an antiparticle made of, starts to shift. We're no longer asking what tiny grains are packed inside it. We're asking what sort of thing it is in the language physics actually uses when it gets serious. Still, before we go further into that, it helps to linger a while with the human intuition, because intuition is not the enemy here. It is just sometimes early. Imagine you'd grown up only ever seeing left-handed gloves. Every shop sells left-handed gloves. Every coat pocket contains one. Every lost glove by the roadside is left-handed, which would at least make winter a little more predictable. Then one day someone presents you with a right-handed glove. Your first thought would not be about deep symmetries in manufacturing. You would ask what this new item is for, whether it is defective, and why the thumb is in such a suspicious position. Only after looking carefully would you see that it is not made of anti-wool. It is not composed of mirror fibres from an inverted sheep. It is a counterpart. Same sort of object, different handedness. Antiparticles are not gloves, mercifully, and they do far more interesting things than sit in drawers waiting to be separated from their partners in the wash. But the comparison helps with the first mental adjustment. Opposites in physics are often opposites of property, not opposites of material. A particle and its antiparticle may have the same mass, the same spin, the same general status in the laws of nature, yet differ in charge and in certain other quantum properties. That is already a little strange, because it suggests that what truly defines one of these entities is not what it is made from in the everyday sense, but the bundle of characteristics it carries. Now, one of the loveliest things about this subject is that the universe did not reveal antimatter in the way one might expect. No one first discovered it by stumbling across a cave full of anti-rocks and wondering why the equipment bill suddenly exploded into light. The idea arrived through theory before it arrived through direct observation. That alone gives it a particular character. It was not merely found, it was, in a sense, anticipated by the mathematical structure of physics. Certain descriptions of particles seem to imply that nature allowed not just one version of a thing but a mirrored partner. That is an extraordinary situation. It suggests that antiparticles are not an afterthought or an error or a decorative flourish. They are woven into the logic of the theory. That detail matters because it pushes against one of the common instincts people have when they first meet the concept. We often assume ordinary matter is the real cast and antimatter is the bonus material in the special features section. Matter gets the leading role because we are made of it, surrounded by it, and rather attached to remaining in one piece. Antimatter then feels like the odd extra, rare and dangerous and perhaps slightly unnecessary. But from the standpoint of the laws that describe elementary particles, the existence of antiparticles is not some exotic side note. It is deeply natural. In fact, one could almost say it is ordinary matter that has simply won the local election in our part of the cosmos, and that local victory can make us forget how strange the whole setup really is. Around you right now are objects that seem perfectly solid and straightforward. A chair, a blanket, a wall, perhaps a mug that was once full of something warm and now contains only ambition. These objects feel reassuringly normal, yet all of them are built from particles that, according to our best understanding, have corresponding antiparticles. The world seems stable not because antiparticles are impossible, but because matter and antimatter are not casually mixed in equal everyday abundance around you. If they were, ordinary housekeeping would become an extreme sport. One does not want to discover that one has accidentally stored anti-cutlery in the wrong drawer. There is also something quietly humbling in the fact that the question, what is an antiparticle really made of, ends up pointing back toward a broader issue. What is any fundamental particle really made of? If we say an electron is fundamental, then as far as present evidence goes, it is not built from smaller parts, in the way a proton is built from quarks. And if the electron has an antiparticle, called the positron, then the positron is not built from anticrumbs of something smaller either. Both are elementary in the current theory. Both arise as basic excitations of a field. Both are, in that sense, equally fundamental. The difference lies not in hidden interior furniture, but in how the laws classify and relate them. That may sound less tactile than the ordinary idea of being made of something, but it is no less real. Physics has repeatedly taught us that reality is under no obligation to remain easy to picture. There was a time when atoms seemed like the final indivisible grains of matter. Then atoms turned out to have internal structure. Protons and neutrons then turned out to have internal structure too. So it is natural to ask whether electrons and positrons are also made of something smaller. At present, no evidence says they are. Perhaps someday a deeper layer will be uncovered. Physics has surprised us before and will no doubt do so again when it's feeling energetic. But within the framework that currently works extremely well, the most accurate answer is not that antiparticles are built from opposite tiny chunks. It is that they are fundamental entities described by the same deep theory that describes particles. Even that phrase fundamental entity deserves a slow moment, because it can sound more mystical than it really is. It does not mean mysterious blob beyond human understanding. It means that in the theory we use, this thing is treated as basic. We do not model it as composed of smaller ingredients. We assign it properties, we observe how it behaves, and we see that those behaviours fit together with enormous precision. In the case of antiparticles, those properties include the remarkable feature that when they meet their corresponding particles, under the right conditions, both can be converted into other forms, often producing light or other particles. This is one reason antimatter has such a reputation. It makes quite an exit. Matter can go about its business quietly for years. Antimatter tends to be remembered for its social interactions, but there is a risk in letting that dramatic ending define the whole subject. If all we picture is annihilation, then antiparticles become little more than the bringers of disappearance. In truth, their existence tells us something richer. They reveal that the universe may encode balance at a deep level. They show that the categories we use, particle and antiparticle, are not arbitrary labels pasted onto unrelated items. They are linked by symmetry and by the structure of the laws themselves. When we ask what an antiparticle is made of, we are really pressing on the question of what makes a thing itself. Is it the material inside it, or is it the full set of properties and relations that the laws of physics recognize? That is not abstract for the sake of being clever. It has practical consequences for understanding the world. A proton and an antiproton, for instance, are not treated as different because one contains normal hardness and the other contains anti-hardness. They are distinguished by measurable properties, and for particles that are not composite, the distinction is even cleaner. An electron and a positron share mass but carry opposite electric charge. That is not a cosmetic difference. It changes how they respond to fields, how they interact, what structures they can form, and what happens when they encounter one another. Identity in particle physics is inseparable from these traits. Asking what something is made of while ignoring its defining properties would be like asking what music is made of while refusing to discuss sound. There is another comforting point here, especially if antiparticles have always sounded remote or menacing. They are not violations of nature. They are part of nature behaving exactly as nature does. Positrons appear in certain radioactive processes. Antiparticles are produced in high-energy environments, in particle accelerators, and in cosmic events. They are not fantasy material imported from a science fiction warehouse. The universe knows how to make them perfectly well. It has been doing so without waiting for our permission. In that sense, antimatter is not outside the story of reality. It is part of the same story, one that becomes stranger and more coherent the longer you sit with it. So as we ease further into this subject, it is useful to carry a few quiet corrections with us. An antiparticle is not anti because it hates matter. It is not made of a shadow substance from another dimension. It is not necessarily less real, less fundamental, or less lawful than the particle you already know. And when physicists talk about what it is made of, the best answer may not involve ingredients at all, at least not in the kitchen cupboard sense. Instead, we are drawn toward fields, properties, symmetries, and the surprising fact that the universe often allows a counterpart where our everyday expectations would only have budgeted for one version. That is where the real curiosity begins to take hold, because once you accept that an antiparticle may be just as basic as a particle, the next questions arrive almost on their own. If they are so similar, what exactly makes one the counterpart of the other? Which properties reverse and which stay the same? How did anyone first realize nature might work this way? And why does a universe that seems so full of matter allow these mirror partners at all? Those questions are where the topic starts to become less about an unfamiliar word and more about the architecture of physical reality itself, which is a very large thing to explore gently, and therefore exactly our sort of evening. To begin untangling that, it helps to sit with a simple but slightly unsettling possibility. What if the particles we call ordinary are not alone in the laws of nature? What if each one comes with a counterpart, not a copy in the everyday sense, not a twin who borrows its clothes and denies it afterward, but a partner written into the same deep rules, a particle with the same mass, the same status as a basic ingredient of the world, and yet with certain properties reversed? It is one of those ideas that sounds almost too tidy to be true, which is often how physics first gets your attention. Nature rarely promises neatness, but every so often it offers a symmetry so striking that it feels less like an accident and more like a clue. The first thing to notice is that the idea of a twin is not something physicists invented because they were bored and the laboratory coffee had gone cold. It comes from a serious habit in science, the habit of asking whether the patterns we see are local quirks or signs of something broader. If one kind of particle exists and carries a particular set of properties, could the laws also allow a partner with opposite charge or opposite values of certain internal characteristics? If the answer is yes, then the universe is not merely providing us with a list of isolated objects, it is organizing them. That may sound like a small distinction, but it changes the mood of the whole subject. A list is just inventory. A pattern suggests meaning. We're all used to the world containing opposites of one kind or another, left and right, positive and negative, north and south on a magnet, push and pull. Even in ordinary life, we do not find it especially shocking that some things arrive in paired forms. Shoes do, hands do, arguments on the internet certainly do, So at first there is something oddly familiar in the suggestion that particles might also come with partners. Yet the familiarity is deceptive, because these are not opposites in the simple visual sense. They are not mirror images you could spot by glancing at them over breakfast. They are opposites in the language of physics, which means the difference lies in measurable properties and in how they behave under the rules that govern the microscopic world. Take the electron, one of the best known of all particles, not because most people spend their evenings chatting about it, but because it quietly does an enormous amount of work. It helps make atoms possible, it helps chemistry happen, it helps your phone, your lamp, and whatever machine eventually burned the toast in your kitchen. The electron carries negative electric charge. Now imagine a partner that has the same mass as the electron, the same amount of intrinsic angular momentum, the same basic place in the theory, but positive electric charge instead. That partner exists. It is called the positron. Already the mind starts to wobble a little, because we are trained by everyday experience to think different behaviour should come from different stuff. But here physics says no. The deep relation is closer than that. These two belong together. And once you allow that one example, the question spreads rapidly. If the electron has a partner, what about the proton? What about the neutron? What about the quarks inside protons and neutrons? What about the muon, the tau, the neutrino? Bit by bit you begin to realise that this is not a curious exception attached to one famous particle. It is a broad structural feature. The universe may not just contain particles, but paired possibilities, matter and antimatter versions linked by symmetry. That is a very different picture of reality from the one most of us inherit casually, where matter is just the ordinary substance of the world and everything else is an optional extra in the advanced section of the textbook. There is a temptation at this stage to picture twins in a rather literal way, as though somewhere there is an anti-zoo full of neatly labelled counterparts pacing around their enclosures. Anti-electrons over here, anti-protons over there, perhaps an anti-gift shop doing surprisingly poor business. But the more useful way to think of it is not as two separate collections of objects that happen to resemble one another. It is as a deep rule about what kinds of states the laws of nature allow. If one state exists with certain properties, another may exist with the opposite sign for key quantities. It is the rule that matters first, the inventory second. This is one of those places where language gently causes trouble. The word twin suggests two things that begin the same way and then lead separate lives, like siblings in a family story. But particle counterparts are not twins in the biological sense, and they are not made in pairs because nature enjoys symmetry as a decorative hobby. They arise because the mathematical descriptions we use seem to permit them, and the universe agrees. That agreement is always the crucial test. Physics can entertain many lovely ideas, but only the ones nature actually honours get to stay. The remarkable thing here is that nature does honour this one. Even so, it helps not to rush straight into the mathematics behind it. There is value in staying a little longer with the ordinary intuition, because ordinary intuition asks good questions. Why would the universe do this? Why not simply have one version of each particle and leave it at that? Why bother with counterparts at all? On the face of it, it seems inefficient, the sort of design choice one might query in a meeting. We already have electrons, must we also have positrons? The world is busy enough. Yet this complaint assumes nature is aiming for convenience, which history suggests is not high on its list of priorities. Nature is usually aiming for consistency. If a certain symmetry fits the rules, then the question becomes not why would it exist, but why would it not? Symmetry has a special status in physics because it often reveals what the laws care about. Not symmetry in the decorative sense, like wallpaper matching the curtains, but symmetry in the deeper sense that certain transformations leave the fundamental description intact. Change the viewpoint, shift the frame, reverse the sign of a property, and the laws still make coherent sense. Again and again, physics has found that when a symmetry appears, it is rarely a mere curiosity. It is a structural signal. It tells you something about conservation, interaction, or what kinds of entities must be possible. The idea that particles may have counterparts belongs to this tradition. It hints that the universe is not built as a pile of unrelated ingredients, but as a network of relations. This is also why the notion can feel so satisfying once it settles in. At first it sounds strange, then it starts sounding right. Of course, a negatively charged particle might have a positively charged partner. Of course, if matter exists, antimatter might exist too. The surprise is not that the pairing is possible, but that our everyday experience has trained us to think of matter as the only cast member worth noticing. We live in a region of the universe where ordinary matter dominates the scenery. Tables, trees, oceans, bones, clouds, bread, keyboards, all matter. So naturally our intuition mistakes local abundance for universal exclusivity. We are like someone raised in a town where everyone plays the violin, concluding that brass instruments must be fictional. The more one thinks about it, the more revealing that local bias becomes. Suppose you had grown up in a universe where antimatter dominated daily life. Your furniture would not feel anti to you. Your breakfast would not be anti-toast. It would just be breakfast, and hopefully better than most. The particle we call an antiparticle would be your ordinary particle. The label itself tells us more about our point of view than about the deeper status of the object. That is worth remembering because the word antimatter can quietly smuggle in the feeling that these things are secondary, hostile, or unnatural. In the laws themselves, they are none of those things. They are legitimate members of the same physical framework. Now, there is a subtlety here that makes the idea even more interesting. Not every particle-counterpart relationship is as simple as flipping the sign of electric charge and calling it a day. Electric charge is one of the most visible examples because it is familiar and easy to talk about. But particles also carry other quantum numbers, little labels that help specify what sort of particle they are and how they behave. The counterpart relationship involves those as well. What stays the same and what changes depends on the kind of particle under discussion and the symmetries involved. That is part of why particle physics can seem both elegant and maddening. The guiding idea is clean, but the details insist on being taken seriously. Still, even without diving too deep into those finer points yet, the broad picture is already powerful. The world of particles is not simply a bag of unrelated specks. It is more like a cast with underlying roles where oppositions and pairings are built into the script. An electron is not just a random little charge carrier. It occupies a place in a larger structure that also makes room for a positron. A proton is not just a proton. There is also an antiproton, the same for many others. Each pairing says the laws are doing something systematic. This brings us to another useful correction to ordinary intuition. When people first hear that particles may have counterparts, they often imagine the counterpart as a copy produced later, almost like an after-image. Ordinary particle first, antiparticle second. Original first, inverse addition afterward. But the better view is that the theory treats both as equally basic possibilities. It is not that the universe built the house and then thought it would be fun to add a reverse house across the road. It is that the blueprint already contained both options. Our human habit of ranking one as normal and the other as derivative comes largely from the fact that one is common in our environment and the other is not. And rarity can be misleading. Gold is rarer than dirt, but that does not make it less real. In some physical settings, antiparticles are not especially rare at all. High-energy collisions can produce them. Certain radioactive decays produce them. Cosmic phenomena produce them. The universe is perfectly capable of making these counterparts when conditions permit. Their scarcity in ordinary bulk matter around us is not evidence against their legitimacy. It is evidence that the history of our cosmos unfolded in such a way that matter ended up with the overwhelming local advantage. Why that happened is a tremendous question in its own right, and one of the most fascinating in modern physics, but it is a later question. Before asking why matter won, we have to understand what the contenders even are. There's also something quietly profound in the fact that the twin idea challenges the everyday meaning of opposite. In ordinary speech, Opposites often cancel the identity of the thing itself. Hot and cold feel like utterly different experiences. Full and empty clearly do not describe the same mug, though life sometimes tries both in quick succession. But in particle physics, a counterpart can be opposite in key properties while remaining deeply the same kind of entity. Same mass, same spin, same role in the laws, different sign on charge. This is not the opposition of enemies, it is the opposition of complementary states. That distinction matters because it keeps the idea grounded. We are not talking about cosmic good and evil, matter and antimatter in some melodrama with dramatic lighting. We are talking about symmetry and classification. Once that settles, a richer question appears. If these pairings are so deeply built into the framework, how did anyone first come to suspect it? After all, no human being can stare directly into the microscopic world and simply see these abstract relations with the naked eye. We do not stroll through particle fields on a Sunday afternoon pointing out symmetries to the neighbours. The twin idea had to be earned through theory and experiment, through patterns in equations and then traces in detectors. It is one of those moments in science where imagination, disciplined by evidence, reaches beyond common sense and then gets rewarded for the effort. That reward did not come because physicists were hoping for a magical mirror world. It came because the equations describing particles started to behave as though the existence of counterparts was not optional. When a theory with the right ingredients begins pointing toward new entities you have not yet seen, science enters one of its most exciting moods. There is tension then, a kind of polite suspense. Either the theory is hinting at something real, or it is leading you into a very respectable mistake. In the case of antiparticles, the hint turned out to be real, and when that happens, our sense of what counts as ordinary has to expand. There is another angle here that makes the whole subject feel strangely intimate. We often think of physics as a catalogue of things out there. Stars, atoms, black holes, galaxies, all arranged at a comfortable explanatory distance. But the idea that every particle may have a twin reaches inward as well. The atoms in your body are built from particles whose counterparts also belong to the laws of nature. The very matter that feels so immediate and personal, your hands, your heartbeat, your ability to frown at complicated ideas and then eventually understand them, is only one side of a more general pattern. You're not made from the only kind of stuff the laws allow. You're made from one winning arrangement in a broader possibility space. That's a very large thought to encounter while sitting quietly with a blanket. But physics does enjoy sneaking large thoughts into small moments. The more patiently we approach it, the less exotic the idea starts to feel. In fact, by now it may begin to seem more surprising that anyone would expect the world not to work this way. Of course, the laws might allow a mirrored partner. Of course, the universe might be more balanced in its basic options than our local experience suggests. What looked strange at first starts becoming reasonable, which is often the sign that a scientific idea is settling properly into the mind. It has not become trivial, far from it. It has become coherent, and coherence matters because it prepares us for the next step. It is one thing to say that particles may have twins. It's another to understand exactly what sort of twin we mean. We need to ask what is preserved, what is reversed, and why. We need to move from the broad intuition of pairing to the sharper question of structure. Are these counterparts built from opposite ingredients? Are they separate objects in separate categories? Or are they, in some deeper sense, two expressions of the same underlying field with different properties attached? Once you ask that carefully, the subject becomes even more interesting, because the twin idea stops being a curious label and starts becoming a window into how modern physics defines identity itself. And that is where the story begins to tighten, because the next step is not just to notice that a particle may have a counterpart, but to understand what that counterpart actually is, and why the laws seem so determined to make room for it. That is where the story begins to sharpen, because once you accept the possibility that particles may come with counterparts, the next natural question is how anyone first realised this was more than a clever thought. It would be comforting in a way if antimatter had first appeared through some very direct and theatrical event. Perhaps a scientist opening a drawer, finding a glowing opposite pebble, and saying something measured but unforgettable. Reality was subtler than that, and far more impressive. Antimatter was not first discovered because someone physically tripped over it. It was seen first in theory. More precisely, it was seen in the demands of an equation, which is one of the strangest and most beautiful things physics ever manages to do. An equation, after all, does not have eyes. It does not peer into the universe with a magnifying glass and report back from behind a bush. Yet sometimes a good equation, built from the right physical principles, becomes a kind of disciplined imagination. It tells you what the world must allow if the framework is to remain consistent. It does not guess wildly. It does not indulge in fantasy. It simply insists. If you want these laws and those requirements to hold at the same time, then this consequence comes with them whether you were hoping for it or not. That is what happened with antimatter. To understand why this was so remarkable, it helps to picture the state of physics in the early part of the 20th century. Scientists were already dealing with enough conceptual upheaval to make anyone long for a lie down in a dark room. Classical ideas that had seemed solid were starting to give way. Quantum mechanics was revealing that the microscopic world did not behave like a miniature version of everyday life. Relativity was reshaping how space and time were understood. The old confidence that nature would ultimately resemble a tidy clockwork machine had taken several well-deserved knocks. And into that already lively intellectual scene came a young British physicist named Paul Dirac. Dirac had a reputation for brilliance of a particularly austere kind. He was not known for spraying words around the room and hoping some of them landed correctly. He was spare, precise, and deeply mathematical. One gets the sense that if language could have been replaced by a smaller and more elegant device, he might have preferred it. He cared about beauty in physical theory, not beauty in the decorative sense, but in the sense that a good equation should have a kind of inevitability to it. It should fit the world cleanly and reveal something fundamental. This may sound lofty, but in physics it has often been a sensible instinct. Some of the best theories are not just effective, they have a strange internal rightness. The problem Dirac faced was a serious one. Quantum mechanics already had successful tools for describing particles at low speeds, and relativity had already transformed the understanding of space, time, and motion at high speeds. But combining these two frameworks properly was difficult. The electron in particular needed a description that respected both the new quantum ideas and the demands of relativity. The existing equations were useful in limited contexts, but there was a sense that something more complete was needed. Dirac set out to find an equation for the electron that would do the job. Now, in everyday life, equations are not usually spoken of as adventurous. No one says a grocery receipt went on quite a journey this afternoon. But this particular search was adventurous in the best scientific sense. Dirac was not merely adjusting a few mathematical screws. He was trying to build a description of nature that worked under deeper rules than the old ones. It had to capture the electron as a quantum object, but also as one that obeyed relativity. It had to respect the structure of the microscopic world while keeping faith with the cosmic speed limit set by light. This was not the sort of task one completes casually between lunch and the post. What Dirac eventually found was extraordinary. The equation that emerged described the electron in a new way and, in doing so, delivered several surprises. One of them was spin, a built-in property of the electron that earlier approaches had struggled to handle naturally. Spin is one of those words in physics that invites confusion because it sounds as though the particle is literally twirling like a small toy top. It is not that. It is a fundamental kind of angular character that particles possess. Dirac's equation handled it beautifully. Already that would have been a major achievement. But the equation had another consequence, and this one was much stranger. It seemed to allow not only positive energy solutions, which fit nicely with the known electron, but also negative energy solutions. That sounds technical at first, but the conceptual trouble it caused was easy to appreciate. If the electron could occupy endlessly lower energy states, then ordinary electrons ought to tumble downward into those states without limit. Matter as we know it would become unstable in a very embarrassing fashion. The world would not sit quietly in chairs and continue with its errands. It would collapse into absurdity. Clearly, something about these negative energy solutions needed interpretation. This was the moment when a lesser thinker might have grown irritated with the mathematics and looked for a way to sweep the inconvenient part under the rug. Dirac did not do that. He treated the equation seriously. If the structure was correct, then the strange solutions could not simply be ignored because they were awkward. They had to mean something. And this is where the story becomes so unusual. Dirac proposed that these negative energy states were not merely errors or formal nonsense. He developed an interpretation in which the sea of negative energy electron states was filled, and a missing electron in that sea would appear as a particle with positive charge. This idea, often called hole theory, is not how modern quantum field theory is usually explained now, but it was an important conceptual bridge. The crucial point is that Dirac was being pushed toward the existence of a positively charged counterpart to the electron. Same mass, opposite charge. Not because he fancied symmetry for its own sake, but because the equations seemed to demand it. That is the key. Antimatter was not inserted as a decorative flourish. It was forced onto the stage by a theory trying to be internally consistent. That must have been a deeply strange moment. Imagine spending your time trying to write down a better mathematical description of the electron and having the mathematics calmly inform you that there ought to be another particle altogether. It is a bit like sitting down to write a family budget and discovering that the arithmetic insists you also have a second attic. One can understand a certain pause. The world had not asked for a positively charged electron. No one had been wandering around in daily life lamenting the absence of one. Yet the theory said it should be there. At first, even Dirac himself did not fully identify this predicted partner in the modern way. There were stages of interpretation, and early on he considered whether the positively charged counterpart might somehow be the proton. That would have been convenient in one sense, because the proton was already known and positively charged. But the fit was poor. The proton had very different mass from the electron. It was not simply the same particle with opposite charge. Gradually, the implication became harder to escape. The equation was not pointing to the proton. It was pointing to an entirely new particle, a true counterpart to the electron. This is worth lingering over because it shows how theory sometimes works at its best. It does not merely summarize what is already known. It extends beyond it in a disciplined way. When a theory begins to say there should be something else out there, something not yet directly observed, science enters a delicate but exciting state. Confidence and caution have to coexist. You do not want to mistake a mathematical artifact for physical reality. At the same time, you do not want to dismiss a genuine prediction simply because the universe has not yet had the courtesy to place it on your desk. And Dirac's equation was not a flimsy speculation. It was doing real explanatory work. It accounted for important properties of the electron in a relativistic quantum framework. It had power. When a theory is both elegant and effective, its stranger consequences deserve careful attention. That is one reason the prediction of antimatter became so compelling. It was not hanging loose at the edge of the theory. It was attached to the theory's central success. There is something quietly humbling in that. Human beings often like to imagine discovery as a matter of looking harder and harder until nature gives in. Sometimes it is that. Sometimes you build a better telescope or detector and the world reveals something new. But sometimes the path runs the other way around. Sometimes you understand the structure of a theory so well that you realize nature must contain something you have not yet seen. Then the experimenters go out and ask the world whether the theory is bluffing. This partnership between theory and observation is one of the healthiest habits science has. Theory says perhaps the world is like this. Experiment replies, let us find out. The reply, in this case, came not long afterward. In the early 1930s, the American physicist Carl Anderson was studying cosmic rays. those high-energy particles arriving from space and interacting in the upper atmosphere. In a cloud chamber placed within a magnetic field, he observed tracks left by particles moving through the detector. These tracks could reveal the charge and momentum of the particle by the way they curved. Anderson found evidence for a particle with the same mass as an electron but positive charge. This was the positron, the very kind of object Dirac's theory had pointed toward. That confirmation changed everything. Once the positron was observed, antimatter ceased to be a strange possibility living only in the mathematics. It became part of experimental reality. The equation had not been indulging in abstract mischief. It had glimpsed a real feature of the world before anyone else had directly seen it. That is why the story has such a lasting grip on the imagination. It captures a rare moment where mathematics seems almost prophetic, though that word can mislead if it suggests magic. There was no magic here. There was rigorous reasoning, physical principle, and the willingness to trust the implications of a strong theory farther than common sense initially wanted to go. It also changed the status of symmetry in particle physics. If the electron had a counterpart, then perhaps other particles did too. The discovery of the positron made it much harder to treat antimatter as a bizarre one-off curiosity. It suggested a pattern. And once physics spots a real pattern, it does not let go easily. The particle world began to look less like a loose collection of ingredients and more like a structured system in which counterparts were deeply woven into the framework. There is another reason Dirac's equation holds such an important place in this story. It sharpened the meaning of what it is for a particle to be fundamental. The positron was not being imagined as a composite object built from anti-pieces of something smaller. It entered as a counterpart at the same level as the electron itself. This was exactly the sort of thing we were edging toward earlier. When the underlying theory treats a particle and its antiparticle as equally basic possibilities, the question of what one is made of becomes more subtle. The answer does not lie in miniature stuffing, it lies in the structure of the field and the allowed excitations within it. Modern quantum field theory makes this clearer than Dirac's original whole picture did. Today physicists describe particles as excitations of fields, and antiparticles appear naturally within that framework as related excitations with opposite charges and corresponding quantum numbers. The mathematics has been cleaned up and reformulated since Dirac's first breakthrough, but the central historical point remains. His work was the turning point where antimatter emerged not from whim, but from the formal demands of a theory that was trying to describe electrons properly. One might wonder why this story continues to feel so arresting even now, long after positrons became familiar members of the particle family. Part of it is surely the drama of the reversal. We tend to imagine experiment leading and theory following, but here theory leaned forward first. Another part is that the prediction was so conceptually bold. A positively charged electron sounds, at first hearing, like a contradiction or a trick. Yet nature said yes. And when nature says yes to something that initially felt impossible, the range of what we are willing to consider starts to widen. There is also a lesson here about scientific temperament. Dirac did not force the world into a comfortable picture. He followed the implications of his equation even when they led to an unfamiliar conclusion. That kind of intellectual discipline matters because the universe is under no obligation to preserve our first intuitions. Again and again, progress in physics has required the ability to let mathematics and evidence correct the imagination. Not to silence imagination, but to educate it. The imagination that emerges on the other side is better, not poorer. It becomes capable of thinking about things like antimatter without reducing them to fantasy props. And of course, the story has a human side as well. Behind every famous equation is a person working through confusion, possibility and doubt. It is easy in hindsight to tell the tale as though antimatter marched smoothly out of the mathematics wearing a name tag. In reality, the route was more hesitant. Interpretation had to be worked out. Early identifications were imperfect. Experimental confirmation had to arrive. Science is often less like a single trumpet blast and more like hearing a tune emerge slowly from instruments that are not yet fully in step. But when the tune finally becomes clear, it can change the entire room. By the time the positron had been found, the conceptual door had opened for the broader antimatter framework we now take seriously. The equation that first pointed the way had done more than solve a technical problem. It had enlarged the map of reality. It had shown that the laws describing one of the most familiar particles in nature also made room for a partner that everyday experience had not prepared us to expect. That is why Dirac's achievement remained so admired. He was not merely adding detail to known physics. He was helping reveal that nature's inventory was larger and more symmetrical than anyone had guessed. And once that door is open, the next question presses in very naturally. If the equation revealed that an electron has a counterpart, what exactly makes that counterpart different while leaving it so strangely similar? What has changed, and what has stayed the same? That is where the idea becomes more concrete, because now we have to ask not just how antimatter was predicted, but what features define an antiparticle as an antiparticle in the first place. What has changed, and what has stayed the same? That is where the idea becomes less ghostly and more precise, because once the existence of antiparticles is no longer in doubt, the mind naturally wants a clean answer. If an antiparticle is not just a science fiction flourish and not merely a mathematical curiosity, then what exactly makes it different from the particle we already know? And perhaps even more intriguingly, why does it remain so strangely familiar at the same time? The answer begins with a quiet correction to ordinary intuition. In daily life, when two things are different, we usually expect them to differ in obvious material ways. A spoon is not a fork because it has a different shape and a different use. Ice is not steam because it behaves differently and looks different, and one of them is much less welcome in a living room. But in particle physics, identity is not built in quite that everyday way. Particles are defined by a set of properties, and what matters is which properties remain the same and which are reversed. Once you see that, the apparent strangeness of antiparticles begins to settle into something more orderly. An antiparticle is not a random opposite. It is not just a particle wearing a false moustache and insisting on being difficult. It is the corresponding partner of a particle, matched to it in a very specific way. For many important properties, the match is exact. For certain others, the sign is reversed. That combination is what gives antiparticles their peculiar character. They are familiar because so much about them is the same. They are different because a few of the differences matter enormously. Consider again the electron and the positron, because they are the cleanest pair to begin with. The electron has a particular mass. The positron has that same mass. The electron has a particular amount of spin, that built-in angular property, that is not really spinning in the ordinary sense but remains fundamental all the same. The positron has the same spin. The electron responds to forces in ways that reflect its nature as a particle of its kind. The positron does too, in a corresponding way. If you were describing them from a distance with only certain features in hand, they would look astonishingly alike. Yet one carries negative electric charge, and the other carries positive electric charge. That one reversal changes everything about how they interact with the electromagnetic fields and with each other. This is where the phrase strangely familiar starts to feel exactly right. The positron is not a different species in the sense that a fish is different from a bicycle. It is more like the electron reflected through a specific rule. Same mass, opposite charge. Same place in the deeper theory, opposite sign on one of the defining labels. It is familiar because it belongs to the same conceptual family. It is strange because our everyday world trains us to think of opposite charge as a very large difference indeed, and in practical terms it is. One can build no ordinary atom with a positron in the same role an electron plays, at least not for long in the matter-filled world we inhabit. The structural kinship is close, the consequences are dramatic, and charge is only one part of the story. Particles also carry other internal labels, the quantities physicists use to classify what kind of particle something is and how it may behave. For the corresponding antiparticle, those kinds of charges reverse as well. Not everything changes, but the relevant internal numbers that distinguish matter from antimatter do. This is part of why antiparticles are not merely positive versions of negative things, or negative versions of positive things in some shallow sense. They are related through a deeper transformation that preserves the particle type while reversing the appropriate internal attributes. This may sound technical, but the intuition is not too hard to keep hold of if we stay patient. Imagine that a particle is identified not by one badge, but by a full passport. It has a mass, a spin, an electric charge, and various other marks that tell nature how to treat it. An antiparticle receives a passport that matches on some entries and flips others. Same birth date, if you like, but a different stamp in the places that determine how it interacts. It is still recognisably the counterpart of the same underlying kind of entity. Yet it will not be treated as the same traveller at the border. The familiarity becomes even more striking when you look at how symmetrically the laws often treat the pair. In a vacuum, isolated from meddling surroundings, the particle and its antiparticle have the same mass for a reason. If they did not, the deep balance built into the theory would begin to fray. Likewise, their lifetimes under corresponding conditions are expected to match. If one is stable, the other should be stable in the same fundamental sense. If one can decay through a certain interaction, the other can undergo the mirrored version. Physics is not merely saying these two are related in spirit, it is saying the laws are constructed so that the pair fit together with remarkable precision. That is one of the most beautiful aspects of the subject, though beauty in physics is always a dangerous word because it can make things sound softer than they are. This is not decorative symmetry. It has teeth. It means that if the universe allows a particle, it often commits itself to a corresponding antiparticle with equal seriousness. The resemblance is not accidental. It is enforced by the framework, and yet the differences matter enough that when particle and antiparticle meet, the encounter is nothing like two ordinary particles passing one another politely at a bus stop. When the right particle meets its antiparticle counterpart, they can annihilate one another, converting their mass into other particles or into light. That possibility is one reason antimatter has such a dramatic reputation. But even here, it is worth noticing what the drama depends on. It depends on the pair being both deeply alike and critically opposite. If they were merely different particles, like an electron and a proton, the story would be different. If they were simply identical copies, there would be no such special cancellation. The annihilation process is powerful precisely because the pair fit together in this mirrored way. This mirrored structure also helps explain why antiparticles are not best understood as ordinary particles with a few cosmetic alterations. A positron is not an electron that has somehow had its charge repainted. The antiproton is not a proton that has been through a regrettable accident in a laboratory. The relationship is more fundamental. They are paired solutions within the same deep description of nature. The antiparticle is built into the identity of the particle itself, in the sense that the theory that gives you one also gives you the other. There is something satisfying in that once it really sinks in. The universe does not seem to do half-hearted opposites. It does not say, here is an electron and then perhaps, on alternate Thursdays, a vague positive cousin if conditions are favourable. It says here is a kind of fundamental entity, and here is the corresponding partner that follows when you reverse the appropriate internal labels. That is more systematic and, in a way, more generous than intuition first expected. Still, familiarity can be misleading if it encourages us to think the pair are interchangeable in all settings. They are not. Put an electron near a proton, and the proton carrying positive charge can bind with it to help form ordinary hydrogen. Put a positron in that same setting and the story changes. The positron will not settle into the familiar role the electron plays. It may briefly form an exotic bound state with an electron called positronium, a kind of miniature atom-like system that lives only briefly before annihilation. That is a lovely example because it shows both the familiarity and the difference at once. The positron is similar enough to the electron to enter a recognizable kind of structure, yet different enough that the structure follows a very different fate. You can see the same theme with protons and antiprotons. They have the same mass, they have the same magnitude of charge, but opposite sign. They have the same spin. They behave in mirrored ways under the same physical laws. Yet bring a proton and an antiproton together, and they do not build ordinary matter. They annihilate into showers of other particles. So the familiarity is real, but it is not the familiarity of peaceful coexistence in our matter-dominated surroundings. It is the familiarity of perfect correspondence. That phrase matters because people sometimes hear that antimatter is the opposite of matter, and imagine that everything about it must be reversed in a vague, almost theatrical sense. Perhaps anti-apples fall upward. Perhaps anti-people would age backward and be impossible to invite to dinner. Physics is much more exacting than that. Antiparticles do not have opposite mass. They do not respond backward to time in the ordinary way people imagine. They are not negative existence. They have positive mass and positive energy in the way we observe them. They move through the world according to the same general laws. The differences are specific, not magical. This precision is one reason the topic is so rewarding. It asks us to replace a cartoon notion of opposites with a more disciplined one. In the ordinary imagination, opposite often means completely unlike. In particle physics, opposite may mean matching in almost everything except a set of key internal properties. That is subtler and, frankly, much more interesting. It is closer to the kind of order nature actually seems to prefer. There is also a historical reason this can feel unfamiliar even after it is explained. Our world is made almost entirely of ordinary matter. That means our brains evolved and our daily language developed in an environment where matter looks like the default and antimatter looks like the exception. We're not used to seeing positrons bouncing around in the kitchen or antiprotons hiding in the garden shed. So our language quietly nudges us into thinking of matter as normal and antimatter as a special effect. But from the standpoint of the fundamental laws, the pair are on far more equal footing than our experience suggests. In fact, one of the quickest ways to loosen that bias is to imagine a region of the universe built from antimatter instead. If there were anti-atoms, anti-molecules, anti-stars, and anti-dust arranged into stable, large-scale structures away from ordinary matter, the inhabitants of such a place would not feel as though they lived in a sinister mirror realm. Their chemistry, in the broad mirrored sense, would proceed according to the same kinds of laws. Their equivalent of an electron would be what we call a positron, and to them it would be ordinary. The familiarity would be complete from the inside. The difference would only become catastrophic if one world met the other directly. That thought experiment is useful because it reminds us that familiarity in physics is partly local. The laws do not privilege our personal comfort, they permit structures. We happen to live in one kind of large-scale arrangement, and that arrangement teaches us what to call normal. But normality is not a fundamental category, it is a local habit. Another subtle point begins to appear here as well. When physicists say a particle and antiparticle are related, they do not always mean that the particle must be distinct from its own antiparticle in the way the electron is distinct from the positron. There are special cases in the particle world where the relationship becomes more delicate. Some neutral particles may possibly be their own antiparticles, depending on the deeper detail of how nature has arranged them. That is a remarkable possibility, though not one to rush into too quickly here. It is enough for now to notice that the concept of antiparticle is not a blunt instrument. It is part of a refined classification scheme, and the details can become beautifully subtle. Even without those complications, the core picture already asks a lot from the imagination. We are being invited to think of identity not as a matter of stuff alone, but as a matter of the full set of lawful characteristics an entity carries. That is a demanding change of perspective, because ordinary life trains us to think materially first. What is it made of? What does it feel like? What shape does it have? With elementary particles, those questions have to be reframed. A particle is what it is through its mass, charge, spin, and the way it sits inside the field structure of the theory. Its antiparticle is defined through the corresponding reversal of the appropriate internal properties while preserving the rest. This is also why the question what makes an antiparticle different cannot be answered honestly with a single casual phrase like opposite charge and that is that. Opposite charge is important, yes, but the full answer is deeper. The particle and antiparticle are different in the way the laws assign internal quantum numbers. They are familiar because the underlying theory treats them as mirrored partners with equal mass and matching overall status. Both sides are essential. Emphasize only the difference and antimatter sounds like alien menace. Emphasize only the familiarity, and you miss what makes the pairing powerful. There is a kind of discipline in holding both truths at once. The anti-electron is not the electron, but it is not foreign to the electron either. The antiproton is not the proton, yet it is not unrelated. The relationship is neither sameness nor total otherness, it is correspondence. That word may be the calmest and clearest one available. They correspond under the symmetries of the theory. They answer one another across the structure of the laws, and once you start thinking that way, a great many things become easier to understand. Why do they have the same mass? Because the laws pair them that way. Why do their lifetimes match under corresponding conditions? Because the symmetry demands it. Why do they annihilate when brought together? Because their mirrored properties allow the pair to convert into other allowed forms. Why does the universe look so one-sided if the pairing is so deep? That is a later and much harder question, but it arises naturally only after the pairing itself is clear. There is also a quiet philosophical shift hidden here. Antiparticles teach us that being opposite does not mean being unreal. It does not mean being derivative in the weak sense. The antiparticle is not the discarded shadow of the particle. It is a fully valid state of nature. If anything, the familiarity between the pair is what gives the difference its force. We care that the positron has the same mass as the electron because it tells us the relationship is exacting, not casual. The mirrored structure is so careful that even the deviations from sameness are highly specific. That level of exactness is what makes modern physics feel both demanding and trustworthy. It does not hand out broad mood-based answers. It says this stays the same, this changes sign, this consequence follows, this one does not. When the theory is right, nature obeys with astonishing precision. And in the case of antimatter, that precision is what transformed a strange prediction into a stable piece of our understanding of the world. So we arrive at a clearer picture. An antiparticle is different because certain defining internal properties are reversed. It is familiar because crucial features like mass and spin remain the same, and because both particle and antiparticle are woven into the same deep laws. One is not a crude opposite of the other, one is the corresponding partner of the other. That is a more exact and more satisfying idea than the ordinary language of opposites usually allows. And once that settles, the old question returns in a sharper form. If the antiparticle is so closely related to the particle, then what does it even mean to ask what it is made of? Are we dealing with a different substance, or has the question itself been slightly misleading from the start? That is where the subject turns from pairing to constitution, because now that the relationship is clearer, we can ask more carefully what sort of thing an antiparticle actually is beneath the labels we've been using. That is where the question becomes more honest, because once we stop treating antimatter like a dramatic prop and start treating it like part of serious physics, we have to face a small problem hidden in the wording. What is an antiparticle really made of sounds like a very sensible thing to ask. In daily life, that is how we understand almost everything. What is a table made of? Wood or metal? What is a loaf made of? Flour and water, and perhaps decisions that did not go entirely to plan. What is a planet made of? Rock, gas, ice, metal. We answer by naming ingredients. So we bring the same habit into physics and ask what the antiparticle ingredient must be. Is there some opposite substance? Some antimaterial tucked behind the visible universe like a second pantry with reverse labels on the jars? The short answer, though I know we're not in the habit of being too short around here, is that an antiparticle is not made of a special anti-substance in the everyday sense. For the most basic particles, the better answer is that they are not made of smaller ingredients at all, at least not as far as present physics can tell. They are fundamental excitations of fields. That phrase can sound like something someone says right before the room goes quiet and several people begin regretting their seating choices, but it is the cleanest route to the truth. If we unpack it slowly, it becomes much less intimidating and much more interesting. Start with the ordinary particle. Take the electron. The electron is one of the best tested ingredients in all of physics. We know a great deal about how it behaves. We know its mass. We know its charge. We know how it responds in electric and magnetic fields. We know how it helps build atoms and chemistry and the entire visible furniture of ordinary matter. But as far as experiments have shown, the electron does not seem to be built out of smaller bits. It does not look like a tiny machine with gears inside. It does not reveal substructure when probed. In the current framework, it is elementary. That means not that it is simple in every respect, but that it is treated as basic. Now take the positron, the antiparticle partner of the electron. The positron is not made of antichrons of electron. It is not a small bundle of opposite dust. It is also elementary, same level of description, same kind of status in the theory. So when you ask what the positron is made of, the best answer is not that it is made of some separate antimaterial. It is that it is a basic excitation of the same kind of deep framework that gives you the electron, but with opposite charge and the corresponding reversed internal labels. This is where the older picture of particles as tiny balls starts to become less helpful. If you imagine a particle as a microscopic marble, then you naturally picture its antiparticle as another marble made of another sort of microscopic stuff. But modern particle physics does not really ask us to picture elementary particles that way. It asks us to think in terms of fields. The universe, in this view, is not empty space with little beads moving through it like dust motes in sunlight. It is filled with fields, and what we call particles are localized excitations of those fields, little packets of activity that behave in stable and measurable ways. An analogy helps, though like all analogies it should be used gently and not trusted with the car keys. Imagine the surface of a pond. A ripple on the pond is not made of a special ripple material. It is a pattern in the water. If another kind of ripple appears, it is still not made of new stuff. It is another allowed disturbance of the same deeper medium. Now, particles are not literally water ripples, and quantum fields are not little ponds sitting behind the wallpaper of reality, but the comparison points in the right direction. A particle is not necessarily a tiny chunk of substance in the old solid object sense. It is an excitation of something more basic. An antiparticle, then, is not made of antimatter in the ingredient sense. It is a corresponding excitation allowed by the same field structure. That changes the whole tone of the question. What is it made of becomes less like asking about ingredients and more like asking about category. What sort of thing is it? The answer is that for elementary cases, an antiparticle is a quantum excitation carrying a particular bundle of properties. It has mass, it has spin, it has charge of the opposite sign from its partner. It belongs to the same fundamental framework. The difference is in the lawful pattern of properties, not in a hidden interior stuffing. There is something slightly unsatisfying about that at first, and it is worth admitting it. Human beings like ingredients. Ingredients feel concrete. They let us imagine small pieces adding up to larger ones, and that works wonderfully for many things in nature. Molecules are made of atoms. Atoms are made of electrons and nuclei. Most nuclei are made of protons and neutrons. Protons and neutrons are made of quarks. It is a very tempting ladder, so naturally we ask what comes next. What are electrons made of? What are positrons made of? What is at the bottom of the bottom? Physics, at least for now, answers by saying perhaps this is bottom enough for these particular entities. Not every rung has another rung beneath it. That answer becomes easier to accept when you remember that physics is not refusing to look. It has looked very hard. Over and over, experiments have tested whether particles like the electron show signs of internal size or internal structure, and so far they behave like point-like elementary objects within the theory. That does not mean future physics could never reveal something deeper. Science has surprised itself before and will likely do so again. But within the current best framework, an electron is elementary and a positron is elementary. So if you ask what the antiparticle of the electron is made of, the most honest answer is that it is not known to be made of anything smaller. That said, not all antiparticles are elementary. This is where the question becomes richer rather than simpler, because some particles are composite, which means built from smaller ingredients, and their antiparticles are composite too. A proton, for example, is not elementary. It is made of quarks bound together by the strong interaction. More specifically, it contains 2 up quarks and 1 down quark in the everyday shorthand of particle physics. An antiproton is the corresponding antimatter version. It is made not of ordinary quarks, but of 2 anti-up quarks and 1 anti-down quark. So in that case, asking what the antiparticle is made of does have an ingredient answer. It is made of antiquarks, bound together by the same strong interaction in a mirrored way. That distinction is extremely important, because it stops the whole subject from becoming too vague. Some antiparticles are elementary, like the positron if current theory is right. Some are composite, like the antiproton. So when someone asks what an antiparticle is made of, the answer depends on which antiparticle we mean. If we mean the antiparticle partner of an elementary particle, then the answer is that it is itself elementary. If we mean the antimatter version of a composite particle, then the answer is that it is built from the corresponding anticonstituents. This is one reason the word antiparticle can mislead by sounding too uniform. It covers several cases. The positron is not made of smaller antipieces. The antiproton is. An antineutron is made of antiquarks in the corresponding pattern. An antiatom, if you build one, is made of antiparticles arranged together, so an antihydrogen atom consists of an antiproton with a positron bound to it. So there is a whole scale of structure here. Elementary antiparticles at one level, composite antimatter systems at another, and even larger antimatter assemblies in principle if conditions allow. And yet even when composition enters, the same deeper lesson still holds. What makes something antimatter is not a spooky opposite substance poured into it like reversed custard. It is the use of antiparticle constituents, entities with the same masses as their matter counterparts, and with reverse charges and related quantum numbers. In other words, antimatter is not a separate chemical essence. It is matter built from the corresponding antiparticle building blocks. This helps answer a question people often carry without quite stating it. If an antiproton is made of anti-up quarks and anti-down quarks, then what are those antiquarks made of? As far as we know, nothing smaller. They are elementary, like the quarks they mirror. Again, the ladder reaches a point where current theory says this is one of the basic levels. The antiquark is not made of anti-anti material. Physics is not trying to build comedy through repeated prefixes until everyone loses patience. At some stage, the antiparticle just is a basic thing in the theory. There is another useful way to say all this. In modern particle physics, the deepest language is not really the language of tiny solid objects. It is the language of fields. There is an electron field. Excitations of that field can appear as electrons and positrons. There are quark fields. Excitations of those fields give quarks and antiquarks. In that picture, particle and antiparticle are not built from different substances. They are different manifestations allowed by the same quantum field framework. One may think of them as opposite charge states associated with the same deeper field description. That is why the symmetry is so tight. They are not strangers assembled from different raw material. They are paired outcomes of the same underlying reality. Now, this can raise another sensible question. If particle and antiparticle come from the same deep framework, why do we call one matter and the other antimatter at all? The reason is not that one is real and the other is a trick. It is that when you build larger stable structures from them, you get different large-scale combinations. Ordinary atoms are built from nuclei and electrons. Anti-atoms are built from antinuclei and positrons. The labels matter and antimatter help us track which side of that pairing we're talking about. But underneath that bookkeeping lies the more balanced truth that both sets are equally licensed by the laws. It is also worth being very clear about what does not happen. An antiparticle is not a hole punched in matter. That was part of an older way of visualizing some aspects of the theory in the early history of antimatter, but it is not how the modern picture is usually presented. A positron is a real particle. You can produce it, detect it, track it, and study it. It is not a missing electron pretending to be an object. Nor is it matter moving backward in time in the ordinary storytelling sense people sometimes repeat after hearing a simplified remark from advanced theory. Those phrases can be useful in specific technical contexts, but if taken literally by a general audience, they create more confusion than they remove. The safest plain language view is that an antiparticle is a real particle state with specific properties, not an absence and not a ghostly bookkeeping trick. There is a further point that makes the subject even more grounded. We do not merely talk about antiparticles on paper, we make them and detect them. Positrons are produced in radioactive decay and in high-energy collisions. Antiprotons have been created in accelerators. Antihydrogen has been assembled and studied. So when we say an antiproton is made of antiquarks, or that a positron is elementary, these are not airy philosophical gestures. They sit inside a framework that is tied to concrete experiments. That is always worth remembering with particle physics, because the language can drift toward the exotic very quickly if it is not anchored now and then to the practical fact that people actually do measure these things. And because people do measure them, they can test whether antimatter really behaves as the mirrored counterpart of matter. Does the positron have exactly the same mass as the electron? Does antihydrogen have the corresponding spectrum one expects from hydrogen? Does the antiproton mirror the proton as theory predicts? Those are empirical questions, and the answer so far has been that the symmetry holds with extraordinary precision. That gives us more confidence that when we say particle and antiparticle are built into the same deep structure, we're not merely admiring a nice theory. We are describing something nature actually seems to do. Now, one might still feel the original question pulling at the sleeve. Yes, fields and excitations and all that. But what is the field made of then? That is the kind of question physics always invites and never fully exhausts. At the current level, the field is part of the basic framework. It is not usually treated as being made of smaller material pieces in the way a wall is made of bricks. It is fundamental in the theory. Perhaps a future theory will go deeper. Perhaps what we now call fields will turn out to emerge from something still more basic. That possibility remains open because science is not a religion of final answers. But if we stay within the best tested framework we currently have, the right place to stop is this. Elementary particles and their antiparticles are fundamental excitations of quantum fields. Composite particles and their antiparticles are built from corresponding constituents, quarks or antiquarks, bound together by the relevant interactions. That is a cleaner answer than everyday language first prepares us for, but it is also a more satisfying one once it settles in. It tells us that antimatter is not made of some uncanny opposite goo. It belongs to the same physical world, follows the same general laws, and is described by the same kinds of deep entities. The difference lies in the charges and other internal quantum properties carried by the excitations or constituents. That is enough to make the world of antimatter distinct without making it mysterious in the cheap sense. There is even something reassuring in that. Physics often sounds most frightening just before it becomes most comprehensible. Antimatter for many people lives in the imagination as a dangerous science fiction fuel, or as the substance that makes things vanish with expensive consequences. And yes, when matter meets corresponding antimatter, the results can be energetic in a way that would certainly liven up a dull afternoon. But before that happens, before the famous annihilation, antimatter is simply part of the same general inventory of nature. It can be trapped, studied, classified, and understood. It is not supernatural. It is not beyond reason. It is another expression of how the particle world is organized. And once you accept that, another question starts to grow naturally out of it. If an antiparticle is not made of a strange opposite substance, but is instead the mirrored partner of ordinary matter within the same deep laws, then why does the encounter between particle and antiparticle end in such a dramatic conversion? What is it about their relationship that allows both to disappear as matter and reappear as light or other particles? That is where the story becomes more dynamic, because now that we know what an antiparticle is, we can look more closely at what happens when it finally meets its ordinary counterpart. That is where the story becomes more dynamic, because now that we know an antiparticle is not some separate ghost substance, but a real partner written into the same laws, we can look at what happens when the two finally meet. And this is the moment where antimatter usually earns its reputation, because matter and antimatter do not simply bounce off one another like two people politely avoiding a collision in a supermarket aisle. Under the right conditions, they can annihilate. That word sounds dramatic because the process is dramatic, but it is also one of the most misunderstood ideas in physics. Matter and antimatter do not meet and become nothing. They meet and transform. They stop existing in their original form, and the energy tied up in their mass and motion reappears as other particles, very often as light of extremely high energy. That distinction matters. Vanishes into light is a useful phrase because it captures the visual intuition of what happens, but it can accidentally sound as though physics is describing some magical disappearance act. One moment there is matter, the next moment there is a blank space and a faint smell of burnt logic. That is not the case. Nothing is being casually erased from reality. What changes is the form. The particle and antiparticle cease to exist as that specific pair, and what remains is the energy and momentum carried away in new forms that the laws allow. It is transformation, not an accounting mistake. Still, the transformation is so complete that the old objects are genuinely gone. That is part of why the process feels so striking. In ordinary life, when things interact, they usually survive in some altered but still recognizable way. Two billiard balls collide and continue on. A raindrop hits a window and spreads. A loaf of bread meets a distracted person in a kitchen and becomes toast or a cautionary tale. But the ingredients remain in some obvious sense. With annihilation, the original particle and antiparticle can disappear completely as particles of that kind. An electron and a positron do not crack, bend, or merge into a lumpy compromise. They are converted into radiation, often in the form of high-energy light. This is one of those places where our daily habits of thought struggle a little, because we're used to treating matter and light as very different categories. Matter feels solid, or at least substantial. Light feels immaterial, fleeting, almost decorative. It illuminates things without seeming like a thing itself. But modern physics long ago forced us to give up that neat separation. Light carries energy. It carries momentum. It can be produced and absorbed in exact quanta. It is not just a glow laid over the world like varnish. So when matter and antimatter convert into light, the universe is not abandoning physical reality for poetry. It is moving energy from one lawful form into another. The cleanest example is the meeting of an electron and a positron. They are ideal partners for this story because they are elementary, simple in the particle physics sense, and beautifully matched. Same mass, opposite charge. When an electron and a positron meet at low enough complexity, they can annihilate into photons, the particles of light. Not the soft kind of visible light you might read by in a quiet room, but a much more energetic kind. The details of how many photons appear depend on the exact circumstances, because the laws must respect conservation of energy, momentum, and angular momentum. Physics is exacting about these things. It does not let particles vanish into a vague cloud of maybe. The final state has to balance the books. That idea of balancing the books is essential, because annihilation can sound reckless until you realize how strict it actually is. Nothing about it is sloppy. every quantity that must be conserved is conserved. Electric charge before the annihilation balances to zero, because the particle and antiparticle carry equal and opposite charge. Momentum must still be accounted for in the outgoing light. Energy must still be accounted for. If the pair were moving before they met, that motion contributes too. The outgoing photons are not a random sparkle. They are nature's precise way of ensuring that the transformation obeys every relevant rule. In fact, one reason the process became so important in physics is that it reveals the deep equivalence between mass and energy in a very direct way. Ordinary matter can sit around looking calm and furniture-like, which encourages the mistaken impression that mass is a static sort of stuff, and energy is something more active and glamorous. Annihilation corrects that bias rather forcefully. It shows that the mass of the particles is itself bound up with energy. When the particle and antiparticle disappear, the energy associated with that mass does not go on holiday. It emerges in the products of the annihilation. This is not a metaphor. It is one of the clearest demonstrations that mass is not separate from energy in the old intuitive way. That is why even tiny amounts of matter and antimatter can produce a great deal of energy when they meet. It is also why antimatter became such a favourite of science fiction writers, who are often very fond of anything that sounds both elegant and explosively inconvenient. But the reality is less cinematic and more demanding. Making antimatter is difficult. Keeping it from touching ordinary matter is difficult. Storing it is difficult. Using it casually would be like trying to keep a snowflake safe in a furnace while carrying it through a marching band. The dramatic energy release is real, but so is the practical problem that antimatter does not appreciate physical contact with the world we live in. That practical difficulty itself tells you something about the nature of annihilation. We do not see it happening everywhere around us all the time because our surroundings are overwhelmingly matter. Not a well-mixed soup of matter and antimatter. If there were antiprotons casually wandering through your breakfast table, breakfast would be a far more eventful ritual than most of us prefer. The reason your chair stays a chair and your walls continue being remarkably unglamorous is that there are not large quantities of antimatter mingling with everyday matter in your local environment. The universe, at least in our region, seems to have ended up on one side of the matter-antimatter balance in a very strong way. Even so, annihilation is not a mere laboratory fantasy. It happens in nature and in practical technology. Positrons produced in certain radioactive decays can meet electrons in matter and annihilate, releasing pairs of high-energy photons. This process is used in medical imaging in the technique called positron emission tomography. It is one of those lovely moments where the strangeness of fundamental physics quietly ends up helping doctors look inside the body. A positron is emitted, it travels a short distance, meets an electron, and the resulting photons are detected in a way that allows an image to be reconstructed. The process is deeply exotic at the level of concept and completely practical at the level of application, which is very often how good physics behaves once it grows up. The simplicity of electron and positron annihilation can make the broader idea seem almost too neat. But things become richer when you move to composite particles like protons and antiprotons. A proton is built from quarks, and an antiproton is built from antiquarks. When they meet, the annihilation is more complicated because you are not dealing with two elementary particles alone. The quarks and antiquarks inside them can annihilate in combinations, and the final products are often showers of other particles before any stable or long-lived radiation emerges. It is a much messier affair, though messy only from our human vantage point. Nature still handles it with complete consistency. The process follows the same core principle. Matter and antimatter do not become nothing. Their energy and internal structure are redistributed into new allowed states. There is something worth noticing in that difference. Annihilation is not one single simple mechanism repeated identically for every pair. It is a family of processes governed by the same broad logic. The more internal structure the original particles have, the richer the possible pathways in the final state. So when people say matter and antimatter annihilate into light, that is true as a broad description, especially in the cleanest cases. but the actual route can involve intermediate particles and a more elaborate chain. Physics often rewards the first simple statement and then politely insists that the details be taken seriously afterward. Another misconception that often appears here is the idea that matter and antimatter are somehow pulling toward annihilation, as though driven by a mystical urge to cancel each other out. That makes for lively phrasing, but the truth is more ordinary and more exact. They interact according to the forces and probabilities allowed by the laws of quantum physics. Opposite electric charges, for example, attract in the case of an electron and a positron, which can certainly help them meet. But annihilation is not an emotional destiny built into the particles. It is an allowed interaction that becomes possible when the right particle and antiparticle encounter one another in the right way. The universe is not writing romance. It is enforcing rules, and those rules include some subtlety. An electron and positron can even briefly form a bound state called positronium before annihilating. This is one of those delightful names in physics that sounds as though someone tried very hard to be practical and whimsical at the same time. Positronium is a short-lived system made of an electron and a positron orbiting one another in a way somewhat analogous to an atom. It does not last because the pair ultimately annihilate, but for a brief moment the universe permits this tiny partnership. That short existence is scientifically useful because it gives physicists a clean system in which to test aspects of quantum theory with extraordinary precision. There is a quiet lesson in that as well. Matter and antimatter are not simply enemies that explode on sight in a cartoon sense. Under the right conditions, they can form definite states, live briefly as an organized pair, and only then annihilate. Again, the laws are more structured than the headline version suggests. Even the dramatic interactions have texture. The phrase vanishes into light is still worth keeping, though, because for all the caution and precision, there is something genuinely astonishing about the process. A particle and its corresponding antiparticle, each with mass, each fully real, can turn into pure radiation. If you encountered that idea without the entire history of modern physics behind it, it would sound like the sort of thing someone made up after not sleeping enough and staring too long at a lamp. Yet it is one of the most secure and tested processes in particle physics. Nature really does allow matter to convert completely into radiation when paired with the right antimatter partner. In a sense, annihilation is the perfect answer to the question of how seriously the universe takes the pairing between particle and antiparticle. It takes it so seriously that when the two meet, the distinction between them can be dissolved entirely into other forms. They are not just related on paper. Their relation has dynamical consequences. The partnership is physically active. It changes what can happen in the world, and it changes how we should think about the solidity of matter itself. Everyday life encourages a kind of material confidence. Tables seem solid, stones seem permanent, mountains seem patient. All of that is fine at the scale where we live, but annihilation reminds us that matter is not the final untouchable substance older intuition hoped for. Matter is one way the underlying fields and energies of the universe organize themselves. Under the right conditions, that organization can be undone and re-expressed. The world is stable enough for us to live in precisely because those conditions are not being met continuously in the objects around us. Stability is real, but it is conditional, not absolute. There is another reason annihilation has such a hold on the imagination. It feels almost moral in its symmetry. A particle and antiparticle are so exactly matched and opposed in the relevant ways that when they meet, they can leave behind no matter residue of either one. Neither wins, neither survives as itself. Both give way to a more stripped-down form. It is tempting to speak about that too poetically, but the scientific content is strong enough without embellishment. The symmetry is so exact that the pair can be replaced by radiation while preserving all the quantities that matter. It is a kind of physical closure. At the same time, the closure is never absolute in the sense of ending the story. The light that comes out of annihilation continues on, carrying energy, momentum, and information about the event. In some contexts, that light may later interact with matter scatter, be absorbed, or even under the right circumstances produce new particle pairs. That last possibility is especially important because it means annihilation is not simply a dead end. Matter and antimatter can be converted into radiation, and radiation can in turn, when conditions are right, produce matter and antimatter. The door swings both ways, though not casually and not under everyday conditions. That is where the process becomes even more interesting than its dramatic reputation suggests. Annihilation is not just destruction. It is one half of a deeper reciprocity between particles and radiation. Under one set of conditions, a particle and antiparticle turn into photons. Under another set of conditions, energetic photons can produce a particle, an antiparticle pair. The laws allow exchange. Matter is not a final destination, and light is not merely a messenger. Each can become the other in the appropriate physical circumstances. Once that settles into the mind, the whole universe starts to feel less like a warehouse of fixed objects and more like a lawful traffic between forms. Still, we should not let the grandeur blur the practical fact that annihilation is astonishingly efficient at converting mass into outgoing energy. That is why large-scale contact between matter and antimatter would be catastrophic. It is also why people sometimes leap from the real physics to wildly optimistic ideas about limitless energy sources. But here the universe reintroduces restraint. Antimatter is expensive to produce in energy terms, difficult to store and hard to handle. You do not get to evade the discipline of conservation laws by dreaming harder. Physics is not moved by enthusiasm alone. The process is real, but engineering it on large scales is another matter entirely. What remains, once the dramatic overtones are trimmed back, is a process of extraordinary conceptual clarity. Matter and antimatter meet. Their opposite internal properties allow a transformation. The original particles disappear as those particles. The energy associated with their masses and motion reappears in radiation or other produced particles. All conserved quantities remain accounted for. Nothing mystical has occurred. Yet the result is still astonishing enough to deserve our attention. It also answers in a very direct way the question of why antiparticles are not just ordinary particles with a cosmetic difference. If the relation were shallow, annihilation would not happen in this special way. The very possibility of the process tells you that the pairing runs deep. Particle and antiparticle are defined so precisely in relation to one another that their meeting opens a channel ordinary particle encounters do not. That is why the subject is not merely about labels, it is about structure. And once you see annihilation not as the end of matter but as a conversion between forms, another question steps naturally forward. If matter and antimatter can vanish into light, can light itself produce matter and antimatter in return? Could the universe, under the right conditions, build particles out of pure radiation and do so in matched pairs? That question is the natural partner to annihilation, because the laws of physics rarely enjoy giving you only one direction of a profound process. That question is the natural partner to annihilation, because once you understand that matter and antimatter can turn into radiation, the next thing to ask is whether radiation can run the process the other way, and the answer is yes. Under the right conditions, the universe can create a particle and an antiparticle out of pure energy. This is one of the most important ideas in modern physics, and it is also one of the easiest to state in a way that sounds like fantasy. Light becomes matter, energy becomes particles. Nothing about that sounds especially modest. It sounds like the sort of thing one would expect from a very confident magician, with poor regard for the fire code. But in physics it is real, lawful and measurable. The first thing to be careful about is the phrase pure energy. It is useful, but it can lead the mind astray if we are not attentive. Energy is not a glowing substance floating about in little jars. It is not a fluid that can be poured from one container to another, while someone in a white coat nods approvingly. Energy is a property, a quantity that physical systems carry. Light carries it. Moving particles carry it. Fields carry it. So when physicists say the universe can create matter from pure energy, what they really mean is that energetic radiation, or other energetic fields and particles, can produce new particle pairs if enough energy is concentrated in the right way, and all the conservation rules are satisfied. That may sound slightly less dramatic than the headline version, but it is more accurate and in the long run more satisfying. Physics almost always gets better when the shiny slogans are translated back into rules. The rule here is that if enough energy is available in a local interaction, that energy can be converted into the mass and motion of newly created particles. And because the laws take balance very seriously, those new particles are often created in matched forms, a particle and its antiparticle together. That last part is especially important. The universe does not usually create one lonely electron out of light and call it a day. It creates an electron and a positron together. It does not casually produce a single quark from nothing in isolation. It produces particle content in combinations that preserve the relevant quantities. This is one of the reasons the creation of antiparticles is not some exotic side effect. It is built into how particle production works. If energy is going to become matter, the bookkeeping has to close properly, and the cleanest way for that to happen is often through pair production. There is something deeply logical about that once it settles in. Suppose a high-energy photon, a particle of light, is involved in a process energetic enough to create matter. The final result cannot violate conservation of electric charge, so if the initial situation has no net electric charge, the produced particles must still add up to no net electric charge. One easy way to do that is to create a negative electron and a positive positron together. The charges cancel in total. Nothing has been smuggled in. Nothing has been lost under the carpet. Nature remains exact. That exactness is worth lingering over, because the phrase from pure energy can sound careless if one does not immediately pair it with conservation. The universe is not improvising wildly. It is not taking an energetic mood and turning it into whatever particle happens to be fashionable this season. It is following strict rules. Enough energy must be present. The right interactions must be allowed. Momentum must still be balanced. Charge must still be balanced. Spin and other conserved quantities must be accounted for. The process is generous in what it permits, but never sloppy. This is also where one of the most famous examples appears. Under the right conditions, a sufficiently energetic photon can help produce an electron and a positron. This is called pair production, and the name is wonderfully plain for something so remarkable. It does exactly what it says. A pair is produced. But even this statement benefits from a little care, because a single photon in completely empty space cannot simply turn into an electron and a positron all by itself while satisfying every conservation law. The process usually needs a nearby nucleus or another photon or some other participant to help balance momentum properly. That detail may sound technical, but it captures something important about the universe. Nature does not forbid pair creation. It just insists that the full situation makes sense. This is very often how particle physics behaves. The broad idea is simple and memorable. Light can become matter. Then the details arrive and remind you that physics is not in the business of granting wishes without paperwork. A lone photon in a perfect vacuum cannot freely choose to become a pair if the conservation rules do not close. But bring in the right environment, enough energy, and the appropriate interaction partner, and the process becomes perfectly real. You can almost think of it as the universe needing the table set properly. Energy is necessary, but arrangement matters too. In the vicinity of a heavy atomic nucleus, for example, a high-energy photon may convert into an electron and positron pair, with the nucleus helping absorb some of the recoil and keep momentum balanced. The nucleus is not there as a mystical catalyst. It is there because the laws require the overall event to work as a whole. That is one of the reasons the microscopic world feels so disciplined once you get used to it. Nothing is simply allowed because it sounds exciting. It is allowed because the full event respects the structure of the laws. This pair production process is not merely a theoretical curiosity. It is observed and used. High-energy physics experiments produce particles and antiparticles all the time by concentrating energy in collisions. In accelerators, particles are pushed to tremendous speeds and smashed together. The incoming energy does not remain neatly confined to the original particles. It can be redistributed into a whole spray of new ones, including antiparticles. In those collisions, the universe is effectively being asked the question again and again. If enough energy is packed into a small enough region, what new particle content are your laws willing to permit? The answer is often a busy and rather enthusiastic assortment. There is a certain fairness to this. Earlier we watched matter and antimatter meet and turn into radiation. Now we see radiation, or energetic collisions, turning back into matter and antimatter. The relationship runs both ways. The universe is not treating matter as sacred and light as merely decorative, or light as sacred and matter as expendable. It allows conversion in either direction when conditions are right. That reciprocity is one of the strongest clues that our old everyday categories were too rigid. Matter is not one sort of everlasting stuff, and radiation another unrelated sort. They are different expressions of a deeper physical economy. And in that economy, antiparticles are not rare exceptions inserted only for the sake of symmetry. They are part of the natural output when energy becomes particle content. If you give the universe enough energy in the correct circumstances, it quite happily produces both sides of the pair. In fact, this is one of the cleanest reasons not to think of antimatter as bizarre or unnatural. The world makes it routinely when pushed into energetic conditions. It is not struggling to produce something alien. It is doing what the laws say. This becomes even more striking when you step away from the laboratory and think about the early universe. There was a time just after the beginning of cosmic expansion when temperatures and energies were vastly higher than anything we commonly encounter now. In that environment, particle creation and annihilation were not rare special events in controlled apparatus. They were part of the ordinary traffic of existence. Radiation could produce particle-antiparticle pairs, and those pairs could annihilate back into radiation. Over and over, in a dense and hot environment, the balance between energy and matter was active, dynamic, and ongoing. That picture helps make the universe feel less like a static container of objects, and more like a place where forms were still being negotiated. At very high energies, the distinctions we now experience as stable and familiar were part of a much busier exchange. Electrons and positrons could be created and destroyed. Quarks and antiquarks could appear in dense, energetic conditions. The early universe was not made of quiet, completed things. It was made of interacting fields and particles in rapid conversation, constantly transforming as temperature and density changed. That history matters because it means the existence of antiparticles is not some later add-on to a matter-dominated universe. They were present in the cosmic story from very early on. The laws did not invent them for the benefit of accelerator physicists. They were there from the beginning, created naturally whenever energy and conditions permitted. In the hot early universe, matter and antimatter were both part of the standard business of reality. This also sharpens one of the biggest later mysteries. If the universe was so good at creating particle-antiparticle pairs, why do we now see so much ordinary matter and so little antimatter on large scales around us? That question remains one of the great unsolved issues in physics, but you can feel its force more clearly now. The laws that create matter from energy tend to create antimatter right alongside it. Pair production is impartial in that sense. It does not seem to have an everyday preference for one side. So something in the history of the cosmos must have tilted the balance, however slightly in favour of matter. That is a later problem, but it grows directly out of the fact that the universe knows perfectly well how to make both. Before getting too far ahead though, it helps to stay grounded in the mechanics of production itself. Pair creation requires enough energy to account for the masses of the produced particles, plus any kinetic energy they carry afterward. This is why not every beam of light is out there creating electrons and positrons as it pleases. Ordinary visible light does not have remotely enough energy per photon to do this. Your bedside lamp is safe from turning the room into a particle factory, which is probably a relief. The conditions have to be extreme enough, and that is why high-energy cosmic rays, energetic gamma radiation, and particle accelerators are the places where such things become relevant. Even then, the identity of what gets produced depends on how much energy is available. If there is enough to create an electron and a positron, that may happen. If still more energy is packed into the interaction, heavier particle-antiparticle pairs can be produced. Muons and antimuons, quarks and antiquarks, and other combinations become possible when the budget is high enough and the interaction allows it. The universe is not limited to one template. It produces what the available energy and the interaction rules permit. In that sense, energy is like a budget, and the particle world is a menu with strict prices and stricter management. That image is slightly silly, but useful. The menu is not chosen by whim. Every possible produced particle has a cost in mass and in the conditions required for its creation. A low-budget event cannot order the heavy options. A high-budget collision can access richer possibilities. This is why particle accelerators are such powerful tools. They let physicists raise the available energy and see what new forms of matter and antimatter the universe is willing to produce. Each increase in energy opens more of the menu. There's another point here that is easy to miss. When energy produces a particle and antiparticle pair, it is not making matter out of a blank absence. The process occurs within fields, interactions, and real physical conditions. This matters because popular language sometimes says particles pop out of nowhere, which is catchy but unhelpful. They do not pop out of nowhere in the ordinary sense. They arise from energetic interactions within the framework of quantum fields. That framework was already there. The energy was already there. The conditions were already being enforced. The particles are new excitations, not uncaused miracles. This is especially useful to remember when people speak loosely about the vacuum. In modern physics, the vacuum is not mere nothingness in the everyday sense. It is the lowest state of the fields, not an empty box in the philosophical sense of total absence. So when energetic conditions create particles from what looks to us like empty space, it is still a process governed by the real structure of the fields. The universe is not performing a trick with literal nothing. It is reconfiguring what the fields can do when energy is present in the right way. That may sound like a subtle distinction, but it protects the subject from drifting into nonsense. Antiparticles are not magical exceptions to reason. They are what the fields and interactions naturally permit. Once you keep saying that quietly enough times, the whole topic starts to feel less like science fiction and more like the lawful behaviour of a world that is simply more flexible than common sense first expected. There is a pleasing symmetry in the whole arrangement. An electron and positron can annihilate into photons. Energetic photons in the right setting can produce an electron and a positron. The same with other particle-antiparticle pairs when energy allows. Matter and radiation are linked by a reversible relationship at the level of possibility, though the details of any specific event depend on circumstances. This is one of the deepest reasons modern physics feels less like a collection of separate facts and more like an integrated structure. Processes fit together. The door you walk through on one side often opens from the other side too. And because the universe can create antiparticles so naturally from energy, it also means that antimatter is not merely something humans manufacture with great difficulty in laboratories. We do manufacture it in small amounts, yes, but nature gets there first and often. Cosmic rays striking the atmosphere can generate antiparticles. Radioactive processes can emit positrons. High-energy astrophysical environments can produce them in significant numbers. Around pulsars, near black holes, in energetic jets, in violent astrophysical events, the creation of particle-antiparticle pairs is part of the physical landscape. Antimatter is not a laboratory novelty. It is part of the energetic grammar of the cosmos. That realization also helps correct the old mental image of antimatter as rare, only because it is almost impossible for nature to make. Nature can make it quite readily when conditions are energetic enough. The real puzzle is not production. The real puzzle is persistence on large scales, in a universe that ended up dominated by ordinary matter. Antimatter is easy enough to create. Keeping large amounts of it separated from matter and assembled into stable bulk structures is another issue. And that brings us to a very natural next step. Once energy creates a particle and its antiparticle, what then? Do they simply rush toward annihilation again at the first opportunity, making the whole exercise feel rather circular? Sometimes yes. In hot, dense conditions, creation and annihilation can chase each other relentlessly. But sometimes the produced antiparticles survive long enough to become parts of larger systems. A positron may briefly bind with an electron. Antiprotons can be trapped. Antiatoms can be assembled. Once that possibility appears, the subject shifts from creation to structure. The question is no longer just how the universe makes antiparticles, but what happens when it gives them enough time and enough isolation to build something more lasting. Once that possibility appears, the subject shifts from creation to structure, because the moment you can make antiparticles and keep them apart from ordinary matter for more than a fleeting instant, a larger question comes quietly into view. Can antimatter build things? Not just isolated particles in a detector, not just brief flashes in a collision chamber. Can it form the same layered kind of world that ordinary matter forms? Can there be anti-atoms, anti-chemistry, anti-clouds, anti-dust, anti-stars, perhaps even entire regions of the cosmos where everything that feels ordinary to us is built from the opposite side of the particle family? The answer begins with something both simple and surprising. Yes, antimatter can form anti-atoms. In fact, once you understand what an atom is at the most basic level, this becomes almost unavoidable. An ordinary hydrogen atom is a proton with an electron bound to it by electric attraction. The proton carries positive charge, the electron carries negative charge. Opposite charges attract, and the pair can settle into a stable bound state. Now change each ingredient to its antimatter counterpart. Replace the proton with an antiproton. Replace the electron with a positron. The antiproton carries negative charge. The positron carries positive charge. Opposite charges attract again. The logic is the same. The structure is mirrored. What you get is anti-hydrogen. That alone is worth pausing over because anti-hydrogen is not a metaphor. It is not a theoretical doodle in the margin of a notebook. It has been made in laboratories. Antiprotons and positrons have been brought together and anti-atoms have been assembled. They are difficult to produce and even more difficult to hold on to because the laboratory around them is made of ordinary matter, and anti-atoms are not known for their talent at peaceful furniture sharing. But the point is that the universe permits such structures. An anti-atom is not forbidden by the laws. It is not unstable simply because it is antimatter. It is unstable in our environment because our environment is overwhelmingly matter. That distinction is very important because it changes antimatter from a dramatic reaction product into a real candidate for structure. It tells us that the electric rules that allow atoms to exist are not biased in favour of ordinary matter alone. They work in mirrored form for antimatter as well. Opposite charges still attract. Bound states still form. Energy levels still exist. The whole general architecture of atomic physics appears to carry over. That is one of the most powerful signs that matter and antimatter are not two unrelated inventions. They are deeply parallel. And once you have anti-atoms, chemistry stops being an absurd question and becomes a serious one. Chemistry, at its heart, is about how atoms combine, share, exchange, and arrange electrons. It is about energy levels, bond formation, molecular shapes, and all the consequences that follow from those things. If anti-atoms have the corresponding structure, then there is every reason to expect anti-chemistry in principle. Antihydrogen could combine with other anti-elements in the same broad mirrored way that hydrogen combines with ordinary ones. Anti-carbon and anti-oxygen could in principle form anti-molecules. The logic of bonding does not collapse simply because the particles involved belong to the antimatter side. The electric interactions are still there, the masses are still the same kinds of quantum rules should apply in mirrored form. That is one of those ideas that sounds more outrageous than it really is. Perhaps it is because the phrase anti-chemistry conjures an image of laboratory glassware filled with liquids that hiss contemptuously at one another, while the staff edge slowly toward the door. In reality, anti-chemistry would not be chemistry with an attitude problem. It would be chemistry built from anti-atoms. If an anti-hydrogen atom behaves as the counterpart of hydrogen, then the broader chemical behavior of larger anti-systems should mirror that of ordinary systems. There is no reason to expect the periodic table to become whimsical, simply because every particle has been replaced by its counterpart. An anti-oxygen atom should not suddenly decide that it would rather act like anti-potatoes. The structure of the laws is too strict for that sort of nonsense. Of course, one has to be careful. Saying anti-chemistry is possible in principle is not the same as saying we can currently set up full antimatter laboratories and leisurely explore anti-molecules the way we explore ordinary compounds. The practical obstacles are formidable. Making enough antimatter is difficult. Trapping it is difficult. Preventing it from touching the walls is difficult. Doing precision chemistry while everything involved must be kept from normal contact is about as straightforward as trying to knit a scarf while riding a bicycle through a pond. It is not impossible in the absolute sense, but it is not an efficient afternoon. Still, science has made meaningful progress in this direction. Anti-atoms have been trapped long enough to study some of their properties. Researchers have compared aspects of antihydrogen with ordinary hydrogen to test whether the deep symmetries expected by theory really hold. That is not just a technical curiosity. It is a direct test of whether antimatter obeys the same basic laws as matter in the ways our best theories predict. So far, the picture strongly supports that mirrored behavior. Antihydrogen does not appear to be some unruly exception. It appears to be hydrogen reflected through the antimatter transformation, just as the theory says it should be. That is a remarkable conclusion, because it implies that the world-making machinery of physics is broader than our daily surroundings suggest. The ordinary world feels so completely matter-based that it is easy to mistake that local dominance for universal design. But anti-atoms quietly tell us otherwise. They say the laws of structure are more neutral than that. They allow organisation on both sides. Ordinary matter did not receive exclusive rights to complexity. And once you start thinking about complexity, the imagination naturally tries to go larger. If anti-atoms can exist, then can anti-molecules exist? If anti-molecules can exist, then could there be anti-dust, anti-ice, anti-water, anti-rock, anti-planets, anti-stars? In principle, yes. Provided enough antimatter were gathered together and kept largely separate from ordinary matter, the same broad story of structure should unfold. Electromagnetic attraction would still allow anti-atoms to bond. Gravity would still pull antimatter together into larger bodies if antimatter has the same gravitational behavior we expect, which all current evidence strongly supports. Nuclear processes inside anti-stars should be the mirrored version of those in ordinary stars. An anti-star would not shine blackness or emit anti-moonlight. It would radiate ordinary photons because light is its own kind of universal messenger in that sense. An anti-star would look from far away disturbingly ordinary. That is one of the strangest and most instructive parts of the whole subject. A world made of antimatter would not necessarily look like a nightmare version of our own. It would not be all sharp angles and ominous humming. If you could stand within an antimatter environment, while also somehow not annihilating immediately, the local experience could be completely normal. Anti-atoms would bind into anti-molecules. Anti-chemistry would build anti-materials. Anti-biology, in principle, might build anti-living systems if all the other immense conditions were met. The local inhabitants of such a world, were such a thing to exist, would regard their environment as ordinary. It would only become catastrophic when brought into direct contact with our matter-dominated world. That realization has an almost philosophical effect on the subject. It reveals how much of what we call normal is a matter of local composition, not fundamental privilege. We're used to thinking of matter as the standard version of reality, and antimatter as the exotic counterpart. But in the laws themselves, the balance is much more even. The terms matter and antimatter reflect our cosmic neighbourhood and its history more than they reflect some deeper hierarchy. If an anti-world existed in isolation, it would not feel anti from the inside. It would feel like a world. There is also something wonderfully sobering in the idea that an anti-star seen from a great distance would be hard to distinguish from an ordinary star by casual observation alone. Antimatter is not neon evil matter carrying a warning label visible from orbit. It follows the same basic physics in so many respects that large-scale anti-structures could masquerade, from a distance, as ordinary ones. This is part of why the question of whether anti-worlds exist is not a childish one. It is a legitimate astrophysical question. If there are large antimatter regions in the universe, how would we know? One possible answer is that boundaries where matter and antimatter meet should produce energetic radiation from annihilation. So one thing astronomers look for is not antimatter glowing differently by itself, but the signatures of interaction where opposite domains touch. That brings us to the possibility of anti-worlds in the cosmos. Could there be entire anti-galaxies, anti-star systems, anti-planets, perhaps tucked far enough away that they have avoided extensive contact with ordinary matter? The honest scientific answer is that it is not impossible in the bare logical sense, but there is currently no strong evidence that our nearby observable cosmic environment contains large antimatter domains of that kind. The large-scale universe we observe appears overwhelmingly matter-dominated. If huge neighbouring antimatter regions were common, we would expect to see more signs of annihilation at the boundaries between matter and antimatter clouds. We do not see the cosmos lit up in that particular way on the scales that would make anti-worlds nearby an easy conclusion. That does not make the idea foolish, it makes it constrained. Physics often works like that. A possibility may remain open in principle, while the observational evidence pushes it farther away, narrows the allowed cases, or makes it less likely in the regions we can study best. The universe does not owe us the most dramatic option, merely because it would make good television. Still, the absence of easy evidence has only made the deeper question more interesting. If the laws permit antimatter structures so naturally, why did the visible universe end up looking so one-sided? Before we lean too heavily into that mystery, it is worth appreciating what anti-atoms already teach us. They tell us that the rules of atomic structure do not care about our local prejudices. They tell us that opposite charges still produce the same kinds of bound states when the ingredients are mirrored. They tell us that the possibility of matter-building complexity is not unique to ordinary matter. All of that is an enormous amount of information from something as simple, in one sense, as antihydrogen. An antihydrogen is especially useful because hydrogen is the simplest atom. In ordinary physics, it serves as a kind of clean test case, the atom that lets theory stretch its legs in public without tripping over too much internal complexity. Antihydrogen plays the same role on the antimatter side. By studying it, physicists can ask whether the spectrum of light emitted or absorbed by antihydrogen matches the mirrored expectations from ordinary hydrogen. They can ask whether the same quantum rules appear to hold. They can ask whether gravity treats it in the expected way. Each test is, in effect, the universe being asked whether it truly respects the deep equivalence between matter and antimatter that our theories claim. So far, that equivalence has held up impressively well. That is important because if antihydrogen behaved wildly differently from hydrogen in its core atomic properties, our whole understanding of particle symmetry would be in trouble. It would mean the laws are hiding a preference where we thought they were balanced. That would be revolutionary, but the evidence so far has not pointed that way. Instead, Nature seems committed to the mirroring. Matter and antimatter appear to be structurally faithful counterparts. There is also a lovely implication for chemistry if that faithfulness continues all the way up the ladder. Ordinary chemistry depends not just on atoms existing, but on the arrangement of electrons in shells and bonds. If antiatoms mirror those structures with positrons in the corresponding roles, then the periodic behaviour should mirror too. Anti-helium should be the counterpart of helium. Anti-carbon should sit in the anti-version of the same chemical family role carbon plays. Anti-water should have the counterpart of the same molecular geometry and broad behaviour as water, assuming the anti-atoms are assembled and isolated successfully. The same kinds of bonds, the same broad forms, the same chemical possibilities, all mirrored. That is a grand statement, and one should treat it with the right sort of care. In principle is doing a lot of work here. No one is setting an anti-kettle on an anti-stove to see whether anti-tea steeps at a respectable rate. The world is not yet arranged for that sort of domestic experiment, and perhaps some parts of the world should never be. But from the standpoint of the laws, the structure points firmly in that direction. Anti-chemistry is not fantasy chemistry. It is the expected chemistry of antimatter systems, and from there, the mind naturally wanders into anti-biology, which is a very dangerous place for speculation to become either too silly or too mystical. The sober thing to say is that if anti-chemistry can build complex molecules, then nothing in the broad logic of the laws forbids the existence of more elaborate antimatter structures in principle. Whether life built from antimatter could exist is a deeper and far more complicated question, because life is not merely chemistry repeated many times with enthusiasm. It involves stability, reproduction, information, environment, and an extraordinary chain of historical contingencies. But the laws themselves do not appear to contain a sign saying complexity allowed for matter only. That is the important point. The barrier is not fundamental law. The barrier, if there is one, is whether the universe ever produced and preserved antimatter environments large and long lived enough for such complexity to emerge. That is where anti-worlds return as a serious idea rather than a decorative one. If somewhere in the cosmos there were a large antimatter region, isolated from ordinary matter early enough and for long enough, then there is no obvious reason the same broad story of cosmic structure could not unfold there. Anti-gas clouds could collapse under gravity, anti-stars could ignite, anti-planets could form from surrounding disks, anti-chemistry could proceed on anti-surfaces under anti-skies. Again, those anti-skies would look entirely ordinary from within. The photons would be photons, the light would be light. The strangeness is in the bookkeeping of the particles, not in some Gothic makeover of reality. This is a useful reminder that physics often hides profound differences beneath ordinary appearances. Two worlds might be built from opposite categories of particles and still look much the same in the large-scale phenomena of light, gravity, temperature, and structure. The catastrophe only appears when the two worlds meet directly, because then annihilation opens the account. Until that point, each can go about its business as a fully lawful world in its own right. There is something almost unfairly elegant about that. The same laws that make antimatter seem dangerous in contact also make it capable of full structure in isolation. The universe is not contradicting itself, it is being consistent. Difference plus isolation allows complexity. Difference plus direct contact allows conversion. Both outcomes follow from the same underlying rules, and that takes us very naturally to the harder question waiting beneath all of this. If anti-atoms are possible, if anti-chemistry is possible, if anti-worlds are at least possible in principle, then why does our visible universe seem so thoroughly matter-filled? Why do we not see abundant anti-stars or anti-galaxies close enough to announce themselves clearly? Why did one side of this elegant symmetry come to dominate the stage we happen to live on? That is not just a decorative puzzle, it is one of the deepest open questions in the whole story of matter and antimatter, because the laws seem so ready to make both that the cosmic imbalance now looks less like an inevitability and more like a mystery. That is where the mystery becomes much harder to ignore, Because once you accept that antimatter is not a fantasy, not a mistake, not a mere mathematical curiosity, but a real and lawful part of the particle world, the obvious question becomes almost impossible to avoid. Why is nearly everything around us made of matter rather than antimatter? Why does the chair remain a chair instead of annihilating with the floor? Why is the air matter? Why are the stars we study apparently made of matter? Why are we, in all our very matter-based habits and worries and grocery lists, here at all? At first glance, the answer ought to be simple. One might think that perhaps the universe simply prefers matter, the way some people prefer tea and others insist on coffee with the conviction of a minor profit. But physics is usually not in the business of unexplained preferences. If the laws produce particles and antiparticles together so naturally, then a universe full of only matter should feel surprising, not inevitable. In the hot early universe, energy was being converted into particle-antiparticle pairs, and those pairs could annihilate back into radiation. The traffic ran both ways. Nothing about that picture suggests a strong everyday bias toward matter alone. If anything, the cleanest first guess would be that matter and antimatter should have been created in nearly equal amounts, and if that had remained true, the story would have been very short indeed. Matter and antimatter would have kept meeting and annihilating as the universe expanded and cooled. A few photons would have gone on their way. The cosmos would have ended up with radiation, perhaps some leftovers in tiny balanced traces, but not the large amounts of ordinary matter needed for stars, planets, oceans, bread, or people trying to understand particle physics late at night. The fact that any substantial matter remains tells us that perfect balance did not survive. Somewhere in the early history of the universe, matter won by a small margin. That small margin is one of the most important details in the whole story. Matter did not need to crush antimatter in some grand and dramatic landslide. It only needed a tiny edge. Imagine creating a vast crowd of particle-antiparticle pairs, almost perfectly balanced, but with just a few extra matter particles for every enormous number of pairs. Then let the universe cool. Most of the matter and antimatter would annihilate each other away, pair by pair, leaving behind radiation, and just those extra matter particles that had no partners left to meet. All the stars, galaxies, planets, and people we know could then be built from that slight leftover. In other words, the visible world may exist because early on the universe favoured matter by an amount that was tiny in proportion and enormous in consequence. That is a fascinating kind of imbalance because it means the entire large-scale richness of the universe may depend on what sounds, at first, like a bookkeeping error so small it could almost be missed. But physics does not let us call it an error. It was a real effect, and if we want to understand why matter surrounds us, we have to understand how that slight excess came to be. Now, it is important to be honest here. This is not a mystery. Physics is completely solved. There are strong ideas, serious theories, and well-defined conditions that any successful explanation must satisfy. But there is not yet a single neat answer we can place on the table and declare the matter settled. That is part of what makes the topic so interesting. We are no longer walking through territory that feels merely strange. We are walking through one of the places where modern physics still knows enough to ask sharp questions, and not yet enough to answer them fully. The first sharp question is whether the laws of physics treat matter and antimatter exactly equally in every circumstance. For a long time, symmetry suggested they nearly should. A particle and its antiparticle have the same mass. They mirror one another in essential ways. Their atomic structures, where studied, appear to behave with extraordinary similarity. So where could an imbalance enter? The answer is that nature does seem to contain small asymmetries in how matter and antimatter behave in certain processes, not huge asymmetries, not the kind that would leap out in daily life, but measurable ones. Certain unstable particles and their antiparticle counterparts do not always decay in precisely identical ways. This phenomenon is part of what physicists call charge parity violation, usually shortened in conversation to a simpler phrase. It means that the laws are not perfectly indifferent between matter and antimatter in all circumstances. That discovery was a major moment because it showed that the symmetry between matter and antimatter, though deep and powerful, is not absolute in every detail. The universe does have some room for favouring one over the other, but there is an important complication. The amount of asymmetry observed in the known processes of the standard particle framework does not appear large enough by itself to explain the full matter dominance of the visible universe. It is as though nature has admitted, yes, I do bend the rules a little in one direction, but perhaps not enough to account for all the evidence we see in the cosmic outcome. This creates a very interesting situation. We know the explanation cannot just be that matter and antimatter were created in perfectly equal amounts, and then somehow matter simply stuck around by luck. Luck is not a law. There must have been real physical conditions and real mechanisms that generated an excess of matter. We also know the explanation cannot be wildly careless, because the universe is full of structures that depend on this excess being just what it was. So whatever happened must have been lawful, specific, and embedded in the high-energy history of the early cosmos. This is where a Russian physicist named Andrei Sakharov enters the story, not because he solved the whole problem, but because he identified the broad requirements any successful explanation would need. He argued that if the universe begins in a symmetric state and later ends up with more matter than antimatter, then certain things must be true. First, there must be processes that do not conserve baryon number, which is one of the ways physicists keep track of matter content in terms of particles like protons and neutrons. Second, there must be processes that distinguish matter from antimatter, the asymmetry just mentioned. Third, the universe must at some stage be out of thermal equilibrium, meaning it cannot remain in a perfectly balanced state, where every forward process is cancelled cleanly by the reverse one. That may sound heavy, but the logic is actually quite direct. If the laws never allow matter number to change, you cannot generate a net excess from a balanced beginning. If the laws never distinguish matter from antimatter in any process, you cannot end up favouring one side. And if everything remains in perfect equilibrium, then any small gains would be immediately washed out by reverse reactions. So those three conditions are less like arbitrary technical hurdles, and more like common sense translated into the language of early universe physics. What makes this difficult is not understanding the conditions. It is identifying the actual mechanism that carried them out in the real universe. There are several broad ideas. One possibility is that the known physics of quarks and unstable particles contributes part of the answer, but not all of it. Another is that neutrinos, those famously elusive particles that pass through matter with almost insulting indifference, may hold an important clue. There are theories in which heavy neutrino-related processes in the early universe could generate an imbalance in one sector that then gets partially converted into the matter excess we see today. This broad family of ideas is often discussed very seriously because neutrinos already behave in ways that remind us nature enjoys hiding big consequences inside tiny and slippery particles. There are also proposals that new physics beyond the standard model may be required. This phrase, beyond the standard model, appears often in modern particle physics and can sound like a vague cupboard where scientists place all their hopes and half their grant proposals. But here it has a precise meaning. The standard model is our best current framework for elementary particles and their interactions aside from gravity. It works extraordinarily well in a huge number of contexts, but it may not contain enough asymmetry by itself to explain why matter dominates the universe. If that is true, then some additional ingredients, particles, forces, or high-energy processes not yet directly observed may have helped tip the balance. This is one reason the problem of matter over antimatter is not a side question. It is a test of whether our current picture is complete. The visible universe itself seems to be telling us there is a historical fact that must be explained. Matter won. We are the evidence. The stars are evidence. The gas between stars is evidence. Every ordinary object in the room is evidence. That means the theory cannot remain comfortable merely by saying matter and antimatter are elegant partners. It also has to explain why, in the world we actually inhabit, one partner is overwhelmingly more common. There is another layer to this that makes the puzzle even sharper. If large regions of antimatter had survived alongside matter on nearby cosmic scales, we would expect matter and antimatter to meet at the boundaries and produce intense radiation from annihilation. Astronomers have searched for signatures of that kind. While the universe is certainly violent and energetic in many ways, we do not see the broad annihilation patterns that would suggest neighbouring matter and antimatter domains colliding on large scales around us. That pushes us toward the conclusion that our observable cosmic neighbourhood is not a patchwork of equal matter and antimatter territories. It looks mostly matter based throughout the regions we can study well. This observational fact matters because it limits the easy escape routes. One cannot simply say perhaps half the nearby universe is antimatter, and we have somehow failed to notice. On the scales we can examine, the evidence points the other way, so the explanation must be historical rather than merely geographical. The universe did not just sort matter and antimatter into separate adjacent bins and leave both in large equal quantities nearby. It appears to have genuinely ended up matter-dominated, at least in the observable region. At this point, it is helpful to remind ourselves how strange that is. The laws that create particle-antiparticle pairs do so impartially in the most basic sense. The early universe was hot enough and energetic enough for both to be present in abundance. Antimatter can form anti-atoms and, in principle, larger anti-structures. Nothing about the underlying physical possibilities screams matter only. The imbalance is not obvious from the basic inventory. It is a historical outcome. That makes it a cosmological mystery as much as a particle physics one. You cannot solve it by studying one isolated particle alone. You have to understand how the universe evolved, and that brings us back to timing. The excess of matter had to be generated early, before the universe cooled so much that pair creation and annihilation largely stopped dominating the traffic. Once temperatures fell far enough, most matter and antimatter pairs would annihilate, and only the excess would remain. So the relevant asymmetry-producing mechanism must have operated in the hot young universe, when energies were high and exotic processes still possible. That makes direct testing hard. We cannot rerun the early universe on command. We can only recreate tiny parts of its conditions in accelerators, study the cosmic leftovers, and build theories that fit both. One of the more interesting features of this whole problem is that it sits right at the border between the smallest scales and the larger scales. It is about elementary particles, quantum processes, and subtle asymmetries in decay rates. But it is also about galaxies, cosmic history, and the fact that there is enough ordinary matter in the universe to build all visible structure. Few questions tie the tiny and the enormous together so neatly. Why is there something like the ordinary material world instead of a universe where matter and antimatter mostly erased one another away? That is a microscopic question with astronomical consequences. There is also a useful caution here. When people hear that physicists do not yet fully know why matter dominates, they sometimes jump to the idea that perhaps antimatter is somehow secretly impossible in bulk or unstable in a fundamental way. But that is not what the evidence says. Antimatter is not failing because it is weak or unnatural. It is simply not what the early history of our region of the universe left behind in abundance. An antiproton is just as legitimate a particle as a proton. Antihydrogen appears to obey the expected atomic rules. The imbalance is not a failure of antimatter to exist. It is a question of why the cosmic recipe ended with a tiny extra spoonful of matter rather than antimatter. And because the excess needed to be only tiny, the challenge is not merely finding a mechanism that prefers matter a little. It is finding one that prefers matter by just the right amount, and in a way consistent with everything else we know. Too small an effect, and there would not be enough matter left after annihilation to build the visible universe. Too large an effect, and the universe we observe might look very different. Physics is not merely seeking a story. It is seeking the right quantitative story, one that matches the actual cosmic inventory. This is part of why precision experiments matter so much. When physicists study subtle differences between matter and antimatter behavior in particle decays, they are not indulging in obscure detail for its own sake. They are testing whether the known asymmetries fit within the bigger puzzle. When neutrino experiments probe whether neutrinos and antineutrinos behave a little differently under certain transformations, they are not just chasing technical trophies. They are looking for clues about the origin of the matter-dominated universe. These tiny laboratory asymmetries may connect directly to the reason the night sky contains stars instead of a more featureless wash of radiation. It is also why the problem has a certain emotional appeal, even if one tries to stay sober about such things. This is not just another missing particle or another parameter to be pinned down. It is a question about why the world has enough lasting material content for structure, chemistry, planets, and biology. One does not have to become sentimental about quarks to feel that this matters. The imbalance between matter and antimatter is tied to the simple fact that there is a material universe to talk about at all. Still, sentiment does not solve anything, and the universe has a habit of ignoring our emotional investment. So the work continues through observation and experiment. Scientists search for signs of unknown particles or interactions that might have shaped the earlier symmetry. They measure matter and antimatter properties with extraordinary care to see whether any tiny difference has been overlooked. They examine the cosmic microwave background, the large-scale structure of the universe, and the behavior of unstable particles for clues. The answer may end up lying partly in accelerator physics, partly in neutrino studies, partly in cosmology, and partly in theoretical ideas that connect them. There is also a broader lesson here about how science often progresses. We do not always begin with a neat explanation and then go out collecting confirmations. Sometimes the universe presents a fact so basic that it's easy to overlook how deep it is. The fact here is simply that ordinary matter exists in abundance. We are so surrounded by it that its presence feels almost beneath notice. Yet that mundane familiarity conceals one of the great unsolved questions of modern physics. Why this excess? Why this side of the balance? Why did the young universe leave behind just enough matter to build everything we see? That question is what makes antimatter more than a technical footnote. Without it, antimatter could remain an elegant symmetry, a brilliant prediction, a dramatic annihilation process, and a fascinating laboratory achievement. With it, antimatter becomes part of a historical detective story about the origin of the visible universe. Matter did not merely happen to be here. Its presence in overwhelming abundance is a clue, and clues like that tend to drive physics outward into the world, because once the problem is clearly stated, you naturally want to know how scientists actually go looking for the answer. Where do they search for antimatter now? How do they hunt for traces of it in space, in cosmic rays, in accelerator experiments, and in the leftovers of the early universe? That is where the story moves next, because once the imbalance becomes the central mystery, the search itself becomes part of the explanation. That is where the story stops being only a question of theory and becomes a question of search, because once you know antimatter is real, and once you know the visible universe seems strangely short of it, you cannot sit back and admire the puzzle forever. At some point you have to go looking, and the search for antimatter has taken physicists into some of the most unusual corners of modern science. It has taken them into particle accelerators, where tiny fragments of the early universe are recreated for brief instants. It has taken them into space with detectors designed to catch rare particles arriving from violent cosmic events. It has taken them into the afterglow of the early universe itself, where the large-scale pattern of radiation and matter may still preserve clues about how the imbalance was born. One of the first things to understand about this hunt is that scientists are not usually searching for antimatter, in the way one might search for a lost umbrella or a missing sock. They are not expecting to open a cupboard and discover a modest colony of anti-apples beside the cereal. The challenge is subtler than that. Antimatter is difficult to keep around in a matter-filled environment, so even when the universe produces it naturally, it often does not last very long before meeting ordinary matter and annihilating. That means scientists must often search not just for antimatter itself, but for signs of its production, its motion, its trapping, or the radiation left behind when it meets matter. This makes the search a bit like detective work. Sometimes you catch the particle directly. Sometimes you see the tracks it leaves in a detector. Sometimes you infer its presence from the kind of light produced when it annihilates. Sometimes you look for large-scale patterns that would be hard to explain unless antimatter had once been abundant or had survived in certain regions. The methods differ, but the underlying goal is the same. Find out where antimatter exists, how nature makes it, how often it appears, and whether any significant reservoirs of it have survived in the cosmos. Particle accelerators are the most direct place to begin, because they allow physicists to create antimatter under controlled conditions. If you want to study something rare and fragile, there is great value in being able to produce it on purpose, rather than waiting patiently for the universe to drop one on your doorstep. In an accelerator, charged particles are pushed to extremely high speeds and then smashed into targets or into one another. The incoming energy of the collision is so great that the original particle content can be converted into showers of new particles. That includes antiparticles. This is one of the clearest demonstrations that antimatter is not exotic in the sense of being unnatural. If you give the laws of physics enough energy, they make it readily. An accelerator is not persuading the universe to do something bizarre. It is providing the conditions under which pair production and related processes become common. Electrons and positrons can be produced. Protons and antiprotons can be produced. Heavier particle-antiparticle pairs can be produced if the energy is high enough. The detector systems around the collision region then try to reconstruct exactly what emerged, how it moved, how long it lived, and how it decayed. And these detectors are astonishing pieces of equipment. They are built like layered traps for information. A particle may pass through one region and leave an electrical signal. It may curve in a magnetic field in a way that reveals its charge and momentum. It may then lose energy in a particular material, or produce a shower of secondary particles, or decay after a tiny but measurable distance into other particles whose tracks can be reconstructed backward. Out of all this, physicists infer whether the original object was a positron, an antiproton, a short-lived meson containing an antiquark, or something even more exotic. The particles themselves do not arrive wearing badges. The detectors have to identify them by behavior. That is one reason the search for antimatter is so technically rich. You're often looking for tiny events buried in vast numbers of other events. You need exquisite timing, careful calibration, and a great deal of patience. It is not unlike trying to identify one particular violin note in the middle of a thunderstorm, except the thunderstorm is made of subatomic debris, and the violin note may last for less than a heartbeat of a heartbeat. Accelerators have taught us an enormous amount about antimatter. They have let scientists produce antiprotons and store them. They have made it possible to assemble antihydrogen atoms. They have allowed detailed comparisons between matter particles and antimatter particles to test whether they really do share the same mass and mirrored behavior with the precision the theory expects. This matters because if some tiny but real difference showed up where none was expected, it could point toward the mechanism that helped matter dominate the universe. So these collider and trap experiments are not just about proving antimatter exists. That part is long settled. They are about testing the symmetry with extraordinary care. That precision work can sound narrow from the outside, but it goes straight to the heart of the biggest question. If the universe once made matter and antimatter in nearly equal amounts, what broke the balance? If some currently unknown process tipped the cosmic scales, there may be subtle traces of that in the behavior of unstable particles, or in matter-antimatter comparison, so accelerators do two jobs at once. They create antimatter for direct study, and they probe the deeper laws that may explain why so little of it survived on large scales. There is also a special charm to the way accelerators let physicists make tiny pieces of the early universe, not in any grand science fiction sense. No one is building pocket universes under Geneva and forgetting where they left them, but in the fleeting conditions right after a very high-energy collision, the density and temperature of the matter produced can resemble in miniature the sort of extreme environment that existed when the universe was very young. Under those conditions, particles and antiparticles are created in abundance. It is a brief return to a time when matter and antimatter were part of the same busy traffic rather than one side being overwhelmingly dominant. By studying those events, physicists can test how particles emerge from hot dense states, how symmetries behave, and how the laws handle conditions that ordinary life politely avoids. This does not solve the antimatter mystery by itself, but it gives researchers a controlled way to study the physics that would have mattered in the early universe. The young cosmos cannot be rerun, but parts of its behaviour can be explored in the laboratory. Then there is the search in space, which has a very different mood. In an accelerator, you create antimatter on purpose and surround it with equipment. In space, you wait for the universe to send something your way, and try to identify it before it slips past. Cosmic rays are the main actors here. These are high-energy particles travelling through space, often at extraordinary speeds, produced by energetic astrophysical events such as supernova remnants, pulsars, and other violent environments. When cosmic rays strike the upper atmosphere or move through interstellar material, they can generate antiparticles among their products. Positrons and antiprotons are therefore not unexpected guests in the cosmic ray population. The real question is what their abundance, energy distribution, and direction tell us. Are these antiparticles simply the ordinary byproducts of high-energy collisions in space? Or do they point to more interesting sources? A positron detected near Earth might have been created in a pulsar environment. An antiproton might have come from collisions of ordinary cosmic rays with interstellar gas, or perhaps some unexpected population could hint at more exotic physics. The data have to be interpreted carefully, because space is not a neat laboratory. It is a loud and complicated place. That is why instruments flown on balloons, satellites, and space stations are so important. They sit above much of the atmosphere and catch incoming cosmic particles before the air scrambles the evidence too thoroughly. Some detectors use magnetic fields to determine whether a particle curves like a positively charged object or a negatively charged one. Others measure how energy is deposited in layers of material. Some combine multiple techniques to distinguish a positron from a proton, or an antiproton from the far more common clutter of ordinary particles. One of the great hopes in space-based antimatter searches has been the possibility of detecting antinuclei, not just single antiparticles. A positron or antiproton can be produced in many routine high-energy processes, but something like antihelium would be much harder to explain as a casual byproduct. An antihelium nucleus would suggest a more substantial antimatter origin, perhaps even the existence of larger antimatter structures somewhere in the cosmos. That is why searches for antinuclei are so tantalizing. They are not just counting particles, they are asking whether any region of the universe may still host bulk antimatter in a meaningful way. So far, evidence for large nearby antimatter domains remains elusive. The observed universe appears overwhelmingly matter-dominated on the scales we can study well. But the search continues because the consequences of a convincing antinucleus detection would be enormous. It would force us to rethink how matter and antimatter were distributed in the cosmos, and whether hidden antimatter reservoirs have survived in ways current models did not expect. In science, some searches continue not because the answer is likely tomorrow, but because the answer would matter so much if it appeared. There is another reason space matters. Antimatter can act as a messenger from extreme astrophysical environments. Around pulsars, for example, strong electromagnetic fields can accelerate particles to huge energies and may produce electron-positron pairs in significant numbers. Near black holes and in relativistic jets, energetic processes can also generate antimatter. So detecting cosmic antiparticles does not merely tell us about antimatter itself, it tells us about the engines that made it. It is one more example of how the hunt for antimatter overlaps with broader astrophysics. You go looking for one thing and end up learning about the entire neighbourhood. And then there is the early universe, which is not a place we can visit and not an object we can trap, yet remains one of the most important arenas in the whole story. In some sense, the biggest antimatter experiment ever conducted was the beginning of the universe itself. The hot early cosmos made particles and antiparticles in enormous numbers. The imbalance between them, however slight at first, had consequences that shaped everything that followed. So to hunt antimatter properly, scientists also have to hunt the fossil clues left by those earliest moments. One of the richest sources of such clues is the cosmic microwave background, the afterglow radiation left from the early universe when it became transparent enough for light to travel freely. This radiation does not contain little labels saying matter beat antimatter here, but its detailed pattern reveals a great deal about the composition and history of the universe. It helps determine how much ordinary matter exists, how much dark matter exists, how the early plasma behaved, and how tiny fluctuations grew into later galaxies. By combining that information with other cosmological evidence, physicists can infer how much ordinary matter survived and how strongly the cosmic balance must have tilted. This is an indirect hunt, but an extremely powerful one. The early universe cannot be observed at the very first instant in a direct photographic sense, yet its later relics preserve the outcome of the processes that happened there. If the matter excess had been different, the later universe would not look the same. The abundance of light elements formed in the first minutes would be different. The growth of cosmic structure would be different. The radiation background would tell a different story. In that sense, the large-scale universe is full of after effects. It is not a crime scene that has been tidied away. It is a crime scene that became galaxies. There is also a very practical connection between early universe theory and laboratory physics. The mechanisms proposed to explain the matter excess often predict certain kinds of behavior in particles we can study today. That is why neutrino experiments matter. It is why precision studies of unstable mesons matter. It is why searches for rare processes that seem almost absurdly unlikely matter. Each one is a small window onto the question of whether the laws of nature contain just enough asymmetry to explain the cosmic outcome. The early universe may be gone, but the laws that shaped it are still here. This makes the hunt for antimatter unusually broad. In one branch of the search, scientists make antihydrogen and ask whether it falls under gravity the way ordinary hydrogen does, or whether its spectral lines match the expected mirrored pattern. In another branch, teams build gigantic detectors around collision points to watch unstable particles decay and compare matter with antimatter versions in painful detail. In another, instruments ride above the atmosphere counting rare antiparticles from space. In yet another, cosmologists measure relic radiation and elemental abundances to reconstruct the conditions under which matter pulled ahead. It is all one story, but told through very different tools. What ties these efforts together is the recognition that antimatter is not merely an object of curiosity, it is evidence. Its existence tells us the laws of physics are broader than daily life suggests. Its scarcity around us tells us cosmic history took a very particular turn. Its creation in accelerators shows how energy becomes particle content. Its appearance in cosmic rays reveals violent processes in space. Its possible signatures in the sky constrain where large antimatter domains could be hiding, if any exist at all. And its near equality with matter in every tested property makes the surviving imbalance harder and more interesting to explain. There is something almost mischievous about that. The laws make antimatter with ease, pair it with matter in elegant symmetry, and then somehow leave us in a universe where one side dominates. It is as though the universe is perfectly happy to demonstrate the balance in principle while declining to preserve it in practice. That mismatch between what seems natural in the laws and what actually happened in cosmic history is what keeps the hunt alive. Even the failures are useful. Every time astronomers do not find evidence for nearby antimatter galaxies, the range of plausible cosmic arrangements narrows. Every time an experiment shows that antihydrogen mirrors hydrogen just a little more precisely, the space for easy explanation shrinks. Every time collider data agree with the standard expectations in another channel, the mystery becomes more concentrated rather than more diffuse. Science often advances this way, not by receiving a full answer in one glorious moment, but by steadily removing the wrong answers until the remaining possibilities have nowhere left to hide. And for all the sophistication of the technology, there is still something very human about the whole enterprise. We live in a matter-dominated world and have become so used to it that we treat it as background. Then physics comes along and says this background is a clue. The ordinary solidity of your hand, the persistent existence of stars, the fact that the universe did not mostly empty itself into radiation long ago, all of that points back toward a tinier symmetry in the early cosmos that we do not yet fully understand. That is a remarkable thing to discover about reality. The familiar world turns out to be evidence of an ancient imbalance, so the hunt continues in every direction that the laws and instruments allow, upward into space, where detectors wait for rare antinuclei and energetic positrons, inward into accelerators, where matter and antimatter are created, compared, and trapped. Backward through cosmic history, where relic light and elemental abundances preserve the outcome of processes no human eye could witness. Each search is incomplete on its own. Together they form something much stronger, a coordinated attempt to understand not only where antimatter is, but why matter got the last word in the visible universe. And once you reach that point, another kind of question begins to press in. After all the particles, detectors, collisions, and cosmic clues, what do antiparticles ultimately tell us about reality itself? Not just about one missing ingredient in cosmology, but about symmetry, identity, and the strange way the universe seems to write counterparts into its deepest laws while still allowing history to choose a winner. By the time you arrive here, after following antiparticles from theory to experiment, from annihilation to anti-atoms, from the early universe to cosmic searches, the original question has changed shape quite a bit. It no longer feels like a narrow technical question about some odd corner of particle physics. It starts to feel like a question about what sort of world this is, not just what objects exist in it, but how reality is organized underneath the familiar surfaces of ordinary life. Because antiparticles do something unusual to the mind. They begin as a curiosity, then become a prediction, then a measured fact, and eventually they start tugging at much larger ideas. They force us to ask what it means for something to be real, what it means for two things to be opposites, and whether the universe is built more from ingredients or from relationships. That is part of why the subject stays with people. If antiparticles were merely strange particles that happen to appear now and then, the story would still be interesting, but it would not have the same depth. What makes the subject so compelling is that antiparticles are not accidental extras. They are woven into the same framework as the particles that make up the world around us. The electron does not stand alone. The theory that describes it also makes room for the positron. The proton has the antiproton. Quarks have antiquarks. Again and again the laws seem to say that one side of the world is not enough. There is a corresponding side built into the same deep structure. That immediately tells you something important about reality. It tells you that the universe is not simply a pile of independent objects scattered into existence one by one. It is structured. It has pairings, symmetries, correspondences. It is governed by rules that connect things before we have ever noticed the connection in experiment. That is a remarkable fact. Human beings often meet the world through its surfaces. We see chairs and trees and rain and faces and begin from there. Physics, when it goes deep enough, reveals that these surfaces are built on patterns far more exact and far more surprising than common sense would ever have guessed on its own. One of the first lessons antiparticles teach is that identity in physics is not quite what everyday thinking assumes it is. In daily life, we often think something is what it is because of the material it is made from or the role it plays. A spoon is a spoon because of its shape and use. Bread is bread because of its ingredients and because it stops being theoretical and becomes lunch. But at the elementary level, identity is not so much about hidden interior material as it is about a package of lawful properties. Mass, charge, spin, and the full set of internal quantum numbers are what define a particle. Its antiparticle is not made of opposite crumbs, it is the corresponding entity with the relevant properties reversed and the rest preserved. The difference is real, but it is not the difference between one substance and another in the old-fashioned sense. That is not a small point. It suggests that reality may be less about little lumps of stuff and more about allowed states within a deeper framework. When you hear that a particle and its antiparticle can have the same mass and the same spin while differing in charge, you're being invited into a very different picture of what the world is made of. It is no longer enough to imagine tiny pebbles of matter rolling about in emptiness. Instead, you start thinking about fields, excitations, symmetries, and rules. The pebbles fade. The pattern becomes the real thing. That shift is one of the deepest gifts physics can offer, even if it is not always offered with the best bedside manner. It forces you to let go of the hope that reality will always resemble your first visual metaphor. Nature is under no obligation to be picture-friendly. It is under no obligation to present itself as a miniature version of the objects we know at human scale. Antiparticles are one of the places where this becomes very clear. The better you understand them, the less sense it makes to ask what opposite substance they are made of. The better question becomes what structure of the laws permits them, and what that says about the framework underneath both matter and antimatter. Another lesson they teach is that opposite does not mean unreal. That may sound obvious when stated plainly, but it is not how most people instinctively react to antimatter at first. The word anti tends to carry emotional baggage. It sounds adversarial, as though antimatter exists in protest. But antiparticles are not rebels against existence. They are part of existence. They are lawful, measurable, and in many contexts just as stable as their matter counterparts. A positron is not less real than an electron. An antiproton is not a theatrical imitation of a proton. The symmetry is too exact for that sort of hierarchy. If anything, antiparticles reveal how misleading our local habits can be. We call ordinary matter normal because we are made of it and surrounded by it. But the laws do not seem to grant it absolute privilege. They grant it local victory. That local victory matters enormously to us, of course. We are not neutral observers floating outside cosmic history. We are built from the winning side of a very old imbalance. Yet antiparticles force a kind of intellectual humility on us. They remind us that what feels standard from our position may only be one historical outcome among several allowed by the laws. Matter did not become the visible basis of our world because the universe could not have done otherwise. It became the visible basis because something in the early universe tilted the balance. That difference between necessary and historical is profound. It means that some of the most familiar features of the world are not written into existence at the deepest level as absolute truths. They are consequences of events. This is where antiparticles become more than a particle physics topic. They become a reminder that the universe contains both law and history. Law tells you what can happen. History tells you what did happen. The laws allow matter and antimatter. The laws allow anti-atoms and, in principle, anti-chemistry. The laws allow pair creation and annihilation. But history seems to have left us in a universe where one side dominates on observable large scales. Reality, then, is not just the list of possibilities written into the laws, it is the specific path taken through those possibilities. Antiparticles sit right at that intersection. They are lawful possibilities whose scarcity in our surroundings points toward a historical asymmetry we are still trying to understand. They also teach us something about conservation and transformation. In everyday life, it is easy to think of objects as having a kind of self-contained permanence. Even when they break, burn, rot, or melt, we imagine them remaining within the broad category of matter. Antiparticle annihilation breaks that habit. Matter and antimatter meet and convert into radiation or other particles. The original forms disappear. That is not destruction, in the childish sense of things being erased into nothing. It is transformation under strict conservation laws. Energy, momentum, and charge are all accounted for. But the event still has enormous philosophical force. It tells us that what feels solid and permanent is, at a deeper level, a temporary organisation of a more flexible physical world. That is one reason antimatter often lingers in the imagination. It makes visible the traffic between forms. Matter can become light can become matter, and antimatter together. The world is not divided into separate kingdoms that never speak to one another. Its categories are more fluid than that, though never vague. The transformations are not sloppy. They are exact, conditional, and tightly governed. But they exist, and their existence means that reality is less like a cabinet of fixed things and more like a system of lawful rearrangements. There is also a deeper symmetry lesson here. Physics has long found that symmetries are not cosmetic. They are structural. They tell you what the laws care about and what kinds of entities the laws will support. The existence of antiparticles is one of the clearest examples of that. Nature seems to prefer descriptions in which a particle is not merely a lone object, but part of a broader mirrored arrangement. That does not mean the universe is perfectly symmetric in every practical outcome. Quite the opposite. The visible cosmos is full of broken symmetries, local imbalances, and specific histories. But underneath those asymmetries there is often a cleaner framework, one that suggests the world is built from paired possibilities, even when later events choose one side more strongly than the other. That is a very useful distinction, because it helps you avoid two mistakes at once. One mistake would be to imagine the universe as fundamentally chaotic, with whatever structures we see arising from pure accident. Antiparticles argue against that. Their existence points to deep order. The other mistake would be to imagine that deep order guarantees perfect balance in every observed outcome. The matter-dominated universe argues against that. Reality seems to involve both symmetry at the level of law and asymmetry at the level of history. Antiparticles reveal both at once. And then there is the question of emptiness, which antiparticles quietly complicate in one of the most satisfying ways. Ordinary intuition tends to imagine empty space as exactly that. Empty. Nothing there. A blank stage on which particles appear and disappear. But the modern picture is not so bare. Fields are present throughout space, and particles are excitations of those fields. Antiparticles belong to that same framework. They are not invaders entering from outside reality. They are part of what the underlying fields can do. That means empty space is not simply a void, waiting passively for matter to wander through. It is part of the structure that makes matter and antimatter possible in the first place. This matters because it shifts the meaning of what is fundamental. If particles and antiparticles are both excitations of fields, then perhaps the fields are deeper than either. If the fields themselves someday turn out to emerge from something deeper still, then perhaps what is fundamental lies even farther below the categories we currently use. Antiparticles encourage that style of thinking because they show how misleading surface categories can be. Matter felt basic until antimatter revealed a broader pairing. Particles felt like little objects until field theory reframed them as excitations. Every time the subject deepens, the old picture becomes less wrong in practice and less fundamental in principle. That can be unsettling if one is looking for a final solid image to rest on, but it can also be freeing. It means reality may be richer than our first categories, not poorer. It means physics is not taking the world apart merely to leave us with emptiness and technical terms. It is replacing naive pictures with more powerful ones. Antiparticles are one of the clearest signs that the deeper picture is not random abstraction. It works. It predicts real things. It survives experiment. It guides the search for new physics. It helps explain why matter exists at all. They also tell us something about our own place in the universe, though here one should be careful not to become too grand too quickly. The safe and honest point is this: we are built from a leftover. The matter in our bodies, in the earth, in the stars, is not the natural consequence of perfect balance. It is the residue of an early asymmetry. Most matter and antimatter likely destroyed one another in the young universe, leaving behind the slight excess that became everything familiar. That means ordinary existence is not just made possible by the laws, it is made possible by a historical imbalance within those laws. Antiparticles reveal that the solidity of the world around us is, in a very real sense, what remained after a vast cosmic cancellation. That is not a poetic exaggeration. It is a physical statement with enormous consequences. The table, the sea, the tree, the hand, the brain trying to picture all this may all depend on a tiny early surplus of matter over antimatter. If the balance had gone the other way, a mirror universe of antimatter structures might in principle have emerged somewhere else. If the balance had been exact, perhaps neither kind of world would have developed as we know it. So when antiparticles force the question why matter won, they are not leading us into a decorative side issue. They are pushing directly on the conditions that made long-term structure possible. There is also a lesson here about realism and imagination in science. Antiparticles were first glimpsed in theory before they were directly observed. That is one of the places where physics earns both its reputation and its occasional air of arrogance. It dares to trust a theory enough to say the world must contain something new. But the story of antimatter also shows the discipline behind that daring. The prediction mattered because it emerged from a theory that was already doing real explanatory work. The confirmation mattered because experiment then found the predicted particle. So antiparticles reveal something about scientific method as well. Reality can be strange, but not every strange idea is real. What matters is the fit between mathematical structure, physical principle and observation. That is worth remembering now because the subject still points beyond what we fully know. The matter-antimatter imbalance remains an open problem. There may be new particles or new interactions still waiting to be found. Neutrinos may carry part of the answer. Precision measurements may uncover tiny departures that become major clues. Cosmology may yet reveal patterns that narrow the possibilities. In that sense, antiparticles also reveal that reality is not finished yielding its structure to us. They are not just a solved story, they are part of an ongoing one, and perhaps that is the deepest mirror of all. Antiparticles do not simply mirror particles, they mirror our own effort to understand the world. At every stage they ask us whether we are willing to let the universe be more balanced and more complicated than ordinary intuition first allowed. They ask whether we can think of identity without relying on crude substance metaphors. They ask whether we can accept that local normality is not universal privilege. They ask whether we can live with a world where symmetry and asymmetry coexist, where law is elegant and history is messy, where deep structure is orderly but the visible outcome still depends on ancient contingency. Those are not small questions, even if they arrive disguised as a technical discussion about particles with opposite charge. And that is often how physics works when it is doing its best work. It starts with something that sounds narrow and ends by changing how you think about reality altogether. Antiparticles begin as one more entry in the catalogue of subatomic things. They end by showing that the world is not merely built from objects but from relations, symmetries, transformations and histories. So what do antiparticles reveal about reality? They reveal that the universe is more symmetrical than common sense suggests, and more asymmetrical than symmetry alone would predict. They reveal that matter is not the only lawful basis complexity could have taken. They reveal that the distinction between stuff and process is not as firm as it first appears. They reveal that particles are not best thought of as tiny pebbles, but as expressions of deeper fields and rules. They reveal that even the ordinary world around us may owe its existence to a small, early imbalance, whose full explanation still lies partly beyond our grasp. And perhaps most usefully, they reveal that understanding the universe often means learning to ask better questions. Not what is the anti-substance hiding behind matter, but what structure of the laws makes counterparts possible. Not why is antimatter so strange, but why does matter seem so ordinary to us? Not how can two opposites both be real, but what kind of reality makes both necessary? Once those questions take hold, the subject opens outward rather than closing down, and the mirror stops being only about antimatter at all. It becomes a mirror held up to the way physics itself works, patient, exacting, occasionally unsettling, and always quietly asking whether we're ready to see the familiar world as part of something much larger.